Hello there and welcome to Life Beyond Seen, where the world's quieter stories find their way to you at last, carried like cold air under a door. Tonight, we're going somewhere most people will never go. Somewhere that does not appear in travel brochures, does not come up in casual conversation, and does not ask for your attention. It simply exists, enormous and indifferent, at the top of the world, doing what it has always done, which is endure and shape and occasionally swallow whole the things that cross it. We are going to the Barents Sea. Picture a body of water larger than the entire country of Peru. Not a romantic sea, not a warm one. No turquoise shallows, no gentle breezes carrying the smell of salt and sunscreen. This is a sea the colour of pewter on its better days, and closer to iron on its worst. It sits above the northern coasts of Norway and Russia, stretching from the coast of Finnmark in the west, all the way to the remote archipelago of Novaya Zemlya in the east. To the north, it is bounded by the islands of Svalbard and Franz Josef Land. To the south, the Russian mainland. It covers roughly 1.4 million square kilometres, and its average depth is only about 230 metres, which for a sea this size is remarkably shallow. In some places, barely enough to swallow a large building. In others, enough to hide an entire fleet and never give it back. Most people, even people who follow geography and history in the sea, have only a vague sense of where the Barents is. They know it is Arctic. They know it is cold. Some remember it from a history lesson about World War II, or from reading about a Russian submarine that sank in the year 2000. But the full picture, the long accumulation of what this sea has done and what it continues to do, tends to stay out of reach. It does not have the fame of the North Atlantic or the romance of the Pacific. It is simply there, at the edge of the map, doing its quiet and devastating work. Before we go any further, I want to ask you something simple. Where are you listening from tonight? Are you somewhere warm, tucked in with the lights low? Or are you somewhere cold yourself? Maybe with frost on the windows and the heating doing its best. It is a strange thing to think about, that somewhere above us, far to the north, there is a sea that is cold in ways most of us will never experience. A cold that is not uncomfortable. It is dangerous. A cold that does not care what you are wearing or how prepared you think you are. Wherever you are right now, I hope it is warm, and I hope you're comfortable. Because the place we're going tonight is neither of those things. If you enjoy long, slow, carefully told stories about the world's more extraordinary places, please consider hitting the like button and subscribing to the channel. It genuinely helps other people find these kinds of stories, and it lets us keep making them. It takes about 2 seconds, and it means a great deal. Now let's go north. The Barents Sea has a paradox at its centre that is easy to miss if you only glance at a map. On one hand, it is one of the most economically and militarily significant bodies of water on the planet. It sits at the intersection of two of the world's great military powers, Norway and Russia, both of whom regard it with the utmost strategic seriousness. It contains some of the world's largest untapped natural gas reserves. It is home to one of the most productive cod fisheries on Earth. It is the primary operating ground of the Russian Northern Fleet, which is based at Severomorsk on the Kola Peninsula, and which, for most of the Cold War, was the largest naval fleet in the world. The Barents is not a backwater. It is, in a very real sense, one of the pressure points of the modern world, and yet most people could not describe it with any confidence. They could not tell you where the polar front runs, or what a polar low is, or why shallow water can be more dangerous than deep water in a storm. They would not know about the ice that forms on the superstructure of ships in winter, adding tons of weight within hours and threatening to capsize a vessel that was perfectly stable the day before. They would not know about the wrecks. There are hundreds of them, ships from the 17th century and ships from the 20th, wooden hulls and steel hulls, fishing trawlers and warships and submarines, some of them nuclear, still resting on the seafloor right now, in the dark, in water just above freezing. The Barents does not advertise any of this. It does not need to. What draws people there, what has always drawn people there, is the same thing that makes it so unforgiving. It is full of things the world wants. Fish, oil, gas, strategic position, a passage toward the east, toward Asia, toward power. People have been willing to risk their lives for what the Barents offers, and the Barents has been collecting on that willingness for at least 400 years of recorded history, and probably much longer. There is a question that sits underneath all of this, and it is one worth holding on to as we go through the story. The Barents is not especially deep. Its average depth of around 230 metres is modest by ocean standards. The Atlantic, by comparison, averages over 3,000 metres. The Barents is, in some places, little more than a very large, very cold, very rough lake when you think about it in terms of depth. You might expect that to make it safer somehow, more predictable, less able to generate the kind of violence that deep ocean waters can produce. But that is not how it works. And understanding why it is not how it works is really the beginning of understanding the Barents Sea. Shallow water and extreme weather do not cancel each other out. They amplify each other. Waves in shallow water behave differently than waves in deep water. They become steeper, more compressed, more likely to break suddenly. When a storm system drives energy into a shallow sea, that energy has nowhere to go except up. The seafloor itself becomes part of the problem, pushing wave energy upward, making seas that are shorter and more violent than you would find in deeper water under the same conditions. A 10-metre wave in the open Atlantic is frightening. A 10-metre wave in the shallow Barents, with a different shape and a different breaking pattern, can be something else entirely. Then there is the weather. The Barents sits at the boundary between two great atmospheric systems, the relatively mild air that comes up from the Atlantic and the brutal cold that pours down from the Arctic interior. When these systems meet, things happen fast. Storms can develop within 24 hours that would take days to form in other parts of the world. The temperature can drop sharply, the wind can shift without warning, and a sea that was difficult but manageable in the morning can become something close to unsurvivable by afternoon. Sailors who have worked the Barents for decades will tell you that it is not the worst days that kill you. It is the days that start out merely bad and then change. And underneath all of that, underneath the weather and the waves and the ice and the cold, there is the simple fact of remoteness. The Barents Sea is not close to anything. The nearest large hospital from many parts of the sea is hours away by helicopter, assuming the helicopter can fly at all, which in winter conditions is not always a safe assumption. If something goes wrong out there, whether it is a fishing vessel taking on water, or a submarine with a failing reactor, or a cargo ship losing power in a gale, the time between the moment things go wrong and the moment help can arrive is measured not in minutes but in hours. And in water that is near freezing, hours is not a number that offers much comfort. This is the fundamental character of the Barents Sea, not evil, not mythological, not even especially dramatic in the way that stories about dangerous places often try to make them seem. It is simply a place where the physical conditions are extreme, where the geography amplifies those extremes, where the distances are vast, and where human beings have been going anyway for centuries, because the alternative was to leave behind everything the sea offered. Some of those people were explorers, pushing north in wooden ships, trying to find a passage to Asia, or simply to understand what was up there. Some were whalers, following the bowhead whale into the ice because the oil and the bone were worth a great deal of money, and the risks were, in their calculation, worth taking. Some were fishermen, working the rich banks of the Barents because the cod were there and their families needed to eat. Some were sailors in wartime, crossing the sea in convoy because the alternative was to let an ally fall. Some were submariners, running nuclear patrols beneath the surface during the Cold War because that was the assignment and you did not refuse it. All of them encountered the same sea. Not all of them came back from it. The name itself comes from Willem Barents, the Dutch navigator who made 3 voyages into these waters in the 1590s, and whose story we will come to properly a little later. He died here in 1597 near Novaya Zemlya after being trapped in the ice through an Arctic winter. His name has been on this sea ever since, which is a kind of memorial, quiet and permanent, written into every map of the world. There is something worth sitting with for a moment, before we go deeper into the history and the science and the disasters. The Barents Sea is not a place that exists at the edges of human experience in the way that, say, the deep ocean trenches do. It is not unreachable. People live near it. Cities exist on its shores. Murmansk on the Russian side is the largest city in the world above the Arctic Circle, with a population of around 280,000 people. Tromsø, on the Norwegian side, is a functioning modern city with a university and a concert hall and restaurants that serve the local catch. The Barents is not some abstract wilderness beyond the reach of civilization. It is right there, at the edge of inhabited Europe, connected to real towns and real economies and real lives. And yet it remains, in some fundamental way, outside of human control. The infrastructure that surrounds it has improved enormously over the past century. The forecasting, the rescue coordination, the navigation technology, the survival equipment, all of it is vastly better than it was even 50 years ago. People who go out onto the Barents today have tools and knowledge that the whalers of the 1600s could not have imagined. And still the sea takes ships. Still it produces conditions that defeat preparation. Still it reminds anyone who spends enough time on it that the improvements are real, but the sea itself has not changed. That is what makes the Barents worth spending a long evening with. Not just the disasters, though there are disasters enough to fill several evenings. Not just the history, though the history is extraordinary. It is the persistence of it. The way the same forces that sank a Dutch explorer's ship in 1596 were present in some recognisable form when a Russian nuclear submarine went down in the year 2000. The way the cold and the shallow water and the sudden storms and the remoteness keep showing up, century after century, in every story that comes out of this sea. The Barents does not change its character to suit the technology of the people crossing it. That is the thing you have to understand going in. It is not waiting to be solved. It is not a problem with a solution somewhere down the line. It is a place with a nature, and that nature has been consistent across 400 years of recorded human encounter with it. We are going to follow that encounter in some detail tonight. We will look at the physics of the sea, at what makes it structurally different from calmer waters. We will follow the whalers and the explorers who first pushed into it, and then the convoys of the Second World War, which produced some of the most concentrated maritime disaster in history. We will go underwater with the Soviet nuclear fleet, and we will spend time with the Kursk, the submarine that became the symbol of everything the Barents could do to a modern warship and the people inside it. We will look at the fishing industry, which loses vessels and men in the Barents with a regularity that rarely makes international news but never really stops. And we will come up to the present day, to the oil platforms and the search and rescue infrastructure, and the ongoing question of what it means to keep going back to a sea that has never once pretended to be safe. But before any of that, it helps to understand what the Barents Sea actually is, physically, what its geography looks like from the inside, why its particular shape, its particular depth, its particular position between two great weather systems makes it the kind of place that it is. Because the history does not quite make sense without the physics. The disasters do not quite make sense without understanding the conditions that produced them. So let us start there, with the sea itself, with the cold water and the shallow banks and the place where the Atlantic meets the Arctic and things begin to get complicated. The Barents Sea sits at a kind of crossroads that, if you drew it on a map, might not look especially dramatic. There is no obvious choke point, no narrow strait, nothing that announces itself as a place where great forces collide. It is just open water, stretching north and east from the top of Norway and Russia toward the archipelagos and ice fields of the high Arctic. But the map does not show you what is happening beneath the surface, or in the lower atmosphere above it, or in the invisible boundary zone where two entirely different bodies of water press against each other and neither one will give way. That is where the character of the Barents Sea actually lives. And once you understand it, the history that comes after starts to make a different kind of sense. The single most important physical feature of the Barents Sea is something called the polar front. It is not a wall exactly. It is more like a long, unstable seam that runs roughly east to west across the middle of the Barents, somewhere between 74 and 76 degrees north, though it shifts with the seasons and the year. On one side of this seam, Atlantic water flows in from the southwest, relatively warm, relatively salty, carrying heat up from lower latitudes the way the Gulf Stream carries warmth to northwestern Europe. On the other side, Arctic water sits cold and dense, and covered for much of the year by sea ice. These two water masses do not mix easily. They press against each other. And the place where they meet is a zone of constant meteorological instability. The warm Atlantic air moving over the relatively warmer water on its side of the front encounters the cold Arctic air sitting over the ice on the other side, and the result is the kind of atmospheric tension that produces weather quickly and sometimes without much warning. Temperature gradients across the polar front can be steep enough that a ship crossing it in winter might move from conditions that are uncomfortable but manageable into conditions that are genuinely dangerous within a matter of hours. The sky does not always give you much notice. This is one of the things that experienced mariners in the Barents will tell you, that the sea has a way of changing its mind faster than you can change your plans. The Atlantic water that drives all of this enters the Barents Sea through a gap on the southwestern side, between the northern coast of Norway and the southern tip of Svalbard. This gap is known as the Barents Sea opening, and it is essentially the sea's main inlet for both warmth and weather. The current that flows through it, part of the broader North Atlantic current system, is what keeps the southwestern Barents Sea from freezing over entirely in winter, which is why Murmansk, despite sitting well above the Arctic Circle, has an ice-free port year-round. That is genuinely unusual for a city at that latitude. It is also why the Barents is navigable when other Arctic seas are not, which is precisely why so many ships have gone into it across the centuries. The accessibility that the Atlantic current provides is real, but it does not make the sea safe, it just makes it reachable. Now, one of the things that surprises people when they first look at the Barents Sea in detail is how shallow it is. The average depth is around 230 metres, which sounds like a lot until you compare it to, say, the Norwegian Sea immediately to the west, where depths commonly exceed 2,000 metres, or the Arctic Ocean proper to the north, which reaches over 4,000 metres in places. The Barents is essentially a shelf sea, a broad, shallow platform sitting on the continental shelf, and that shallowness has consequences that go far beyond simple depth measurements. Scattered across the floor of the Barents are a series of underwater banks, broad elevated areas where the water is particularly shallow. Spitsbergenbanken, the large bank sitting southwest of Svalbard, rises to depths of only 20 to 50 metres in places. The central bank sits further east, another broad, shallow platform that influences both the currents and the behaviour of storms passing over it. These banks were historically important for fishing because the shallow, nutrient-rich water supported enormous populations of cod, haddock, and other commercial species. They are still important for fishing today, but they are also significant for a less welcome reason, which is what they do to waves. In deep water, ocean waves move relatively freely. They have room to develop their characteristic shape, long and rolling, and a ship in deep water can ride over them with some predictability. In shallow water, things change. As waves approach shallower areas, the bottom begins to interact with the wave's movement. The wave slows at the base while the top continues moving. The wave steepens. It becomes shorter and choppier with a more vertical face. This is called wave steepening due to shoaling, and it is one of the reasons why shallow seas can be rougher and more dangerous than deep ones, even in the same wind conditions. A wave of a given height in the Barents can be more punishing to a vessel than a wave of the same height in the open North Atlantic, because its shape is different. It hits harder, it breaks more unpredictably. The interaction between the Barents' shallow banks and the storm systems that move across it creates wave patterns that can be genuinely chaotic. When a storm moves over a bank, the waves that form there can meet waves reflected back from different directions, and the result is a confused sea state, where swells are arriving from multiple angles simultaneously. For a ship trying to maintain a stable heading, this is exhausting at best and catastrophic at worst. Fishing vessels, which tend to be smaller and sit lower in the water than large cargo ships, are particularly vulnerable to these conditions. A beam sea, where waves are hitting the vessel from the side rather than the bow, can cause a smaller ship to roll beyond its recovery angle in a matter of seconds. It does not require an enormous wave to do this. It requires the right wave at the right moment, and the Barents has a talent for producing exactly that. There is also the question of storm surge. In shallow seas, strong sustained winds can physically push water up against coastlines and shallow banks, raising sea levels locally by a metre or more. This amplifies wave heights and can flood low-lying coastal areas, but it also changes the effective depth over the banks in ways that can affect navigation. A vessel that thought it had adequate clearance over a shallow bank might find, in storm conditions with surge, that the margin has closed considerably. The Barents' geography seems, at times, almost thoughtfully arranged to maximise this kind of risk. The meteorological conditions that act on this geography deserve some attention on their own. The Barents Sea is one of the primary breeding grounds for a weather phenomenon called a polar low. These are small, intense cyclones, sometimes compared to miniature hurricanes, that form over open Arctic water when cold air from the ice moves out over the relatively warmer sea surface. The temperature difference between the cold air mass and the warmer water below it fuels rapid atmospheric convection, and a polar low can develop from almost nothing into a full storm system within 12 to 24 hours. At their peak, polar lows can produce sustained winds exceeding 30 metres per second, which is roughly equivalent to a Category 1 hurricane. They are typically 200 to 500 kilometres across, much smaller than a mid-latitude cyclone, but their speed of development is what makes them so dangerous. A ship's crew can go to sleep in rough but manageable conditions and wake up to something entirely different. What makes polar lows particularly difficult to deal with is that they are notoriously hard to forecast, even with modern satellite technology and numerical weather prediction. They form quickly, over open water, in regions where observation data is sparse. The models that work well for predicting large-scale weather systems in the mid-latitudes struggle with the small-scale, rapid dynamics of polar lows. Forecasters in Norway and Russia, who monitor the Barents Sea, have improved their polar low detection considerably over the past 2 decades, partly through better satellite imagery and partly through dedicated research programs. But even now, the lead time on a reliable polar low forecast is often measured in hours rather than days. For a vessel already at sea, hours can be enough to seek shelter or change course. But it is a thin margin, and not every vessel has the speed or the sea room to use it. The wave heights that these systems can generate are significant. In a severe Barents Sea storm, wave heights of 10 to 14 metres are documented. There are accounts of rogue waves, individual waves that exceed the surrounding sea state by a considerable margin, though these are harder to verify and their frequency in the Barents specifically is not well established in the scientific literature. What is well established is that the combination of steep, shallow water waves and the confused sea states produced by the Barents' irregular bathymetry creates conditions that are harder to survive than simple wave height numbers might suggest. A 10-metre wave in a well-organised swell is a serious challenge. A 10-metre wave arriving from an unexpected direction in a chaotic sea state is something else. There is one more geographical feature worth mentioning, because it affects navigation in a way that is easy to overlook. Near the Novaya Zemlya island chain, on the eastern side of the Barents, there is an atmospheric phenomenon known as the Novaya Zemlya effect. It is a form of superior mirage caused by temperature inversion layers in the Arctic atmosphere, where cold, dense air sits near the surface beneath warmer air above. Under these conditions, light bends in ways that distort what observers see and what radar systems detect. Objects can appear to be in positions they are not. Coastlines can seem closer or further than they are. The effect is well documented, and it has been known to navigators in the region for a long time, but knowing about it and correcting for it in real-time navigation, particularly in poor visibility and rough conditions, are different things. The Barents has a way of making the things you know about it hard to apply in the moments when you most need to. The sea's physical character taken together amounts to something that is genuinely unusual. It is not the deepest sea or the coldest or the most remote. It does not hold records in any single category that would obviously mark it as the world's most dangerous body of water. What it has is a particular combination of features, the polar front and its weather instability, the shallow banks and their effect on waves, the polar lows and their speed of development, the bathymetric complexity that creates confused sea states, the remoteness from infrastructure that makes rescue slow, and the cold water that makes survival time desperately short once a vessel is lost. None of these features is unique to the Barents, but the way they stack together, the way each one compounds the others, is what gives the sea its character. Sailors who have worked the Barents for many years tend to describe it not as a dramatic place exactly, but as an unforgiving one. The word that comes up often is unpredictable. Not wild, not extreme, though it can be both of those things, but unpredictable in a way that resists full preparation. You can have the right equipment, the right training, the right forecast, and the sea can still produce something you did not plan for. The experienced fishermen and naval officers who know it best do not speak about it with contempt or bravado. They speak about it carefully, the way you speak about something that has earned your respect through repeated demonstration of what it can do. That respect was earned over a very long time, and by people who had far fewer tools for understanding the sea than we do now. The first Europeans to push into the Barents in any systematic way were navigating with instruments and knowledge that seem almost impossibly limited by modern standards. They were working with rough charts, magnetic compasses that behaved strangely near the pole, and wooden ships that could not retreat from ice once it closed around them. They were trying to understand a sea whose physical behaviour we have only fully begun to explain in the last 50 years, and yet they went. Some of them went many times, driven by commerce and ambition, and the particular human quality that finds the unknown more compelling than the familiar. What they encountered in the Barents, and what it cost them, is where the human story of this sea really begins. Before any of that human history unfolds, though, there is one more dimension of the Barents Sea's physical character that needs its own careful attention. Because the sea does not just threaten ships with weather and waves and shallow, confused water. It threatens them with something that can arrive silently, that can accumulate invisibly, that can change the weight and balance of a vessel so gradually that a crew might not notice until the situation is already critical. Ice. Not just the ice that blocks a passage or grinds against a hull, but ice in all its forms, and ice in all its behaviours, and ice doing things that people who have never worked in Arctic waters might not immediately think to worry about. The Barents Sea is not the most ice-covered Arctic body of water. The central Arctic Ocean holds that distinction, and the waters around the northern Canadian archipelago are more reliably frozen for more of the year. The Barents sits at a kind of threshold, influenced enough by the Atlantic to remain partially open even in the depths of winter, but far enough north and cold enough that ice is never entirely absent from the picture. What this means in practice is that the Barents occupies a zone of constant seasonal negotiation between open water and ice cover, and that zone shifts in ways that have become harder to predict as the climate has changed. In a typical winter, the southern boundary of sea ice in the Barents can extend as far south as roughly 74 degrees north latitude. To put that in some perspective, that is approximately the latitude of Longyearbyen, the main settlement on Svalbard, and it means that in a cold winter the ice edge can push down into waters that ships transit regularly. In a mild winter, the ice may retreat considerably further north, leaving large areas of the Barents navigable even in January and February. The year-to-year variability is substantial. This is not a sea where you can assume the ice will be in the same place it was 12 months ago, and that variability is itself a navigational hazard, because it means that charts and experience from previous seasons may not accurately reflect what a vessel will encounter. There are 3 broad categories of sea ice that matter for navigation in the Barents, and they behave quite differently from one another. Fast ice is ice that is attached to the shore or to the seafloor in shallow water. It is relatively stable, it does not move with the wind and current, and while it blocks access to coastal areas, it is at least predictable. You can see it on a chart, you can observe it from a distance, and you can plan around it. Pack ice is the large consolidated mass of sea ice that forms in the central and northern Barents during winter. It can be thick, it can be ridged and deformed from the pressure of ice floes pressing against each other, and it is essentially impenetrable for any vessel that is not specifically built as an icebreaker. Ships that are not ice-strengthened do not enter pack ice intentionally, and when they encounter it unexpectedly, the results can be severe. Drift ice is the category that causes the most problems for ordinary navigation, because it is the least predictable of the 3. Drift ice consists of individual floes and fragments of ice that have broken away from the pack and are moving freely under the influence of wind and surface currents. These floes can range from small pieces a few meters across to large sheets hundreds of meters in diameter. They move, they concentrate in areas of converging current, they spread out in areas of divergence, and they can appear in a navigable channel that was clear the previous day. A vessel transiting an area of drift ice has to maintain constant watch, adjust speed to allow time to maneuver around flows, and accept that the situation can change faster than any chart can be updated to reflect. In reduced visibility, in fog or heavy snow, drift ice becomes something genuinely dangerous, because a flow encountered at speed can punch a hole in a hull that is not designed to take the impact. But there is a form of ice-related danger in the Barents that is perhaps less immediately obvious than any of these, and in some ways more insidious. It is called spray icing, or sometimes ship icing, and it has been responsible for the loss of vessels in circumstances where the crew might not have felt themselves to be in immediate danger from the sea state or the weather. The mechanism is straightforward once you understand it, but the speed at which it can develop is alarming. When air temperatures drop below approximately -8 degrees Celsius and wind speeds are sufficient to drive sea spray onto the exposed surfaces of a vessel, that spray freezes on contact. It freezes on the superstructure, on the rigging, on the masts and antennas, on the railings, on the deck equipment, on any surface that is cold enough to hold it. Each layer of ice adds weight. Not a lot at first, but the accumulation is continuous as long as the conditions persist. And in the Barents in winter, those conditions can persist for many hours, sometimes for a full day or longer. The problem this creates is not just about the additional weight in absolute terms, though that matters too. The more critical issue is where the weight accumulates. Ice builds up on the upper structures of a vessel, on the parts that are highest above the waterline. This raises the centre of gravity of the ship. A vessel that was stable in normal conditions becomes progressively less stable as ice accumulates on its upper works, because the weight distribution has shifted in the worst possible direction. The righting moment, which is the force that returns a ship to upright when it rolls, decreases as the centre of gravity rises. A fishing vessel that might comfortably roll 30 degrees and return to upright in calm conditions might, with several tons of ice accumulated above its main deck, roll to that same angle and not come back. The capsize can happen without any sudden change in the sea state. The sea does not need to produce a rogue wave or an extraordinary gust. The ship simply reaches a point where its stability has been compromised beyond recovery, and the next roll is the last one. Estimates of how quickly this can happen vary depending on vessel type, air temperature, wind speed, and sea state. But accounts from fishermen and naval officers who have worked the Barents suggest that a small to medium fishing vessel can accumulate enough ice to significantly affect its stability within a few hours in severe icing conditions. The only solutions are to reduce speed to minimise spray generation, to change course away from the wind and sea to reduce spray exposure, or to physically remove the ice by chipping and breaking it away from the superstructure. That last option, chipping ice in the dark, in freezing temperatures, on a rolling vessel, in the middle of a storm, is exactly as difficult and dangerous as it sounds. Crew members have been lost overboard doing it. The work is exhausting, and the rate of accumulation can exceed the rate at which a small crew can remove it. There are documented cases of vessels in the Barents and in adjacent Arctic waters that capsized and sank while their crews were actively working to chip ice from the upper decks. The Barents Sea's relationship with ice has been changing, and the change is substantial enough that it deserves careful attention. The Barents is one of the fastest warming regions on the entire planet. Sea surface temperatures have risen, the atmosphere above the sea has warmed, and the extent of sea ice has declined sharply over the past several decades. Since the 1970s, when systematic satellite monitoring of Arctic sea ice began, the Barents has lost roughly half of its average winter sea ice extent. Some years have seen ice conditions so reduced that areas which were reliably frozen for months in previous decades remained open water through the entire winter. The trend is clear, and it is continuing. The immediate intuitive response to this information is that a sea with less ice is a safer sea for navigation, and in some narrow specific sense, that is true. A vessel that no longer needs to navigate through drift ice in a particular area has one fewer hazard to contend with. Access to ports like Murmansk and to the northern sea route along Russia's Arctic coast has become easier in summer months. There is genuine commercial interest in the Barents as a transit route as ice conditions have relaxed. But the fuller picture is more complicated, and in some ways more concerning. As ice retreats, the Barents becomes accessible to a wider range of vessels, including vessels that are not designed or crewed for Arctic conditions. A fishing boat or a small cargo ship that would never have ventured into previously ice-covered waters may now operate in areas where the ice has gone, without necessarily having the equipment, training or hull strength to deal with the conditions that remain. The water is still near freezing, the polar lows still develop, the spray icing risk is still present whenever temperatures drop, the shallow banks still produce steep, dangerous wave conditions. The remoteness from rescue infrastructure has not changed. What has changed is that the barrier of ice that previously kept less capable vessels out of these areas is no longer there. The sea has, in a sense, opened a door, and not every vessel that walks through it is prepared for what it finds on the other side. There is also a subtler meteorological consequence of reduced ice cover that researchers have been studying for some time. Open water in the Barents in winter, water that was previously covered by ice and therefore insulated from the atmosphere, releases heat and moisture into the cold Arctic air above it. This additional heat and moisture can influence the formation and intensity of polar lows, though the exact nature of that relationship is still an active area of research. Some studies suggest that a more ice-free Barents may produce more frequent or more intense polar lows under certain atmospheric conditions. The details are genuinely uncertain, and it would be wrong to state confidently that less ice means more storms. But the possibility that the changing ice conditions are altering the sea's weather character in ways that are not yet fully understood is something that meteorologists and oceanographers take seriously. The other thing that retreating ice does is expose the seafloor of the Barents to processes that have been frozen out for a long time. The Barents Shelf contains large deposits of methane hydrates, compounds of methane and water that are stable under cold high-pressure conditions but can destabilize as temperatures rise. There is ongoing scientific monitoring of methane release from the Barents Sea floor, and while the quantities detected so far are not considered catastrophic, the long-term implications for both the sea's chemistry and for the broader climate system are uncertain enough to warrant continued attention. This is a different kind of risk than the navigational and meteorological hazards discussed so far. Slower moving, less immediately dramatic, but potentially significant on longer timescales. What all of this amounts to is a sea in transition. The Barents that exist today is measurably different from the Barents of 50 years ago, and the Barents of 50 years from now will likely be different again in ways that are difficult to fully anticipate. The physical forces that make it dangerous are not disappearing. The cold water remains, the polar lows remain, the shallow bathymetry remains, the distance from rescue infrastructure remains. But the configuration of those forces is shifting, and the population of vessels and people operating in the sea is growing as access increases. The combination of more traffic and persistent hazards is one that maritime safety researchers watch with real concern. There is something almost counterintuitive about the idea that a sea becoming less icy might become more dangerous in certain respects. We tend to think of ice as the threat and open water as the relief. But the Barents has a way of complicating the assumptions you bring to it. The ice was, among other things, a kind of natural boundary that limited who could enter and what they could attempt. As that boundary softens, the sea's other qualities, its weather, its cold, its remoteness, its capacity for sudden and violent change, do not soften with it. They simply become accessible to a larger audience. The people who understood this best, who knew the Barents not from satellite data or climate models, but from years of direct experience, were the navigators and fishermen and traders who worked these waters long before any of those tools existed. And among the earliest of those people, one name stands above the rest, not because he conquered the Barents, but because he tried to understand it, pushed further into it than anyone before him, and ultimately did not come back. His story, and the story of the era of exploration and commerce that he represented, is where the human record of this sea becomes something you can follow in detail, through documents and artefacts and the preserved remnants of a winter camp on a desolate island that was not found again for nearly 3 centuries. Willem Barents was a Dutch navigator, cartographer, and explorer who made 3 separate voyages into the Arctic between 1594 and 1597. He was not a reckless man. He was methodical, experienced, and driven by a specific practical goal, finding a navigable northeast passage above Russia that would allow Dutch merchant ships to reach Asia without passing through waters controlled by the Spanish and Portuguese. The commercial logic was sound. The ambition was reasonable, at least by the standards of the time. What he encountered in the Barents Sea, the sea that would eventually bear his name, was something that no amount of preparation could fully account for. His first voyage in 1594 took him northeast along the Norwegian coast and into the waters above Novaya Zemlya, the long double island that forms the eastern boundary of the Barents Sea. He reached the northern tip of Novaya Zemlya, which he named Ice Cape, and found open water beyond it, which gave him genuine reason to believe a passage was possible. The second voyage in 1595 was a larger, more commercially organised expedition, and it ended in frustration when sea ice blocked the route south of Novaya Zemlya. The backers were disappointed. Barents was not deterred. The third voyage, in 1596, is the one that history remembers most clearly. Barents and his crew sailed north and discovered what they called Spitsbergen, the large island archipelago now known as Svalbard, before turning east toward Novaya Zemlya again. They rounded the northern cape and pushed further east than any European navigator had managed before, but the ice closed in around them faster than they could react. By late August of 1596, their ship was caught and held fast in the ice near the northeastern coast of Novaya Zemlya. It was not going to be freed before winter. What followed was one of the earliest documented cases of European sailors being forced to overwinter in the high Arctic. Barents and his crew of 16 men dismantled parts of their ship and used driftwood and whatever timber they could salvage to construct a shelter they called Het Behouden Huis, which translates roughly as the saved house or the safe house. The name was partly hopeful, partly practical. They spent the winter of 1596 to 1597 in this structure, in temperatures that dropped to -30 or 40 degrees Celsius, in near total darkness for months, hunting polar bears and foxes for food, managing frostbite and illness, keeping records and logs with a discipline that seems almost extraordinary given their circumstances. They survived the winter. In June 1597, as the ice began to break up, they launched 2 small open boats and began making their way west along the coast of Novaya Zemlya, trying to reach the open sea and eventually a port where they could find help. Barents himself was already very ill by this point, weakened by the winter and by what was most likely scurvy, though the exact nature of his illness is not definitively recorded. He died on June 20th, 1597, in one of those small open boats, somewhere off the northern coast of Novaya Zemlya. He was probably in his late 40s or early 50s. The surviving crew members eventually made it to the Kola Peninsula and were picked up by Dutch ships. They brought back Barents's logs and charts, which were detailed enough to be genuinely useful for future navigators. The location of the winter camp was known from the survivors' accounts, but it was not visited again for nearly 275 years. In 1871, a Norwegian sailor named Elling Karlsen landed on the northeastern coast of Novaya Zemlya and found the remains of Het Behuden Huis still standing, partially buried under ice and debris but largely intact. Inside were preserved artifacts from the winter of 1596 and 1597, navigational instruments, books, clothing, a pair of flintlock pistols, a clock, cooking utensils, and a printed copy of a Flemish translation of a Persian travel narrative. The cold and the dryness of the site had kept these objects in a condition that was, by any reasonable expectation, remarkable. Some of them are now in the Rijksmuseum in Amsterdam. When you look at them, you're looking at objects that sat in the Arctic darkness for nearly 3 centuries waiting to be found. What Barents and his crew experienced was a concentrated version of what the Barents Sea routinely delivers: the combination of ice, cold, darkness, distance, and the speed with which conditions can shift from manageable to catastrophic. They were skilled, they were prepared by the standards of their time, they made reasonable decisions, and they still lost their ship, lost their commander, and came very close to losing everyone. The sea did not distinguish between the careful and the careless. It simply was what it was. The Dutch and English whalers who followed in the wake of these explorations learned this lesson repeatedly, and at considerable cost. The discovery of Svalbard opened access to some of the richest whaling grounds in the North Atlantic. Bowhead whales were present in large numbers in the waters around the archipelago, and their slow swimming speed and high oil yield made them commercially valuable targets. By the early 1600s, Dutch and English whaling operations were competing aggressively for access to these grounds, and by the 1610s and 1620s, the industry had grown into something substantial. The Dutch established a whaling station on the northwestern coast of Svalbard at a place they called Smeerenburg, which means something close to Blubbertown in Dutch. At its height in the 1630s, Smeerenburg was a seasonal settlement of several hundred men, complete with brick furnaces for rendering whale blubber into oil, storage buildings, and enough infrastructure to support a significant industrial operation during the summer months. The Dutch alone were sending dozens of ships north each season. The English, Basque, and Danish whalers were also present. The Barents Sea, and the waters around Svalbard in particular, were being worked with a commercial intensity that would have been unimaginable just a few decades earlier. The losses were substantial, and largely unrecorded in any systematic way. Ships were caught in ice, ships were driven onto the shallow banks by storms, men fell overboard in the cold water and were dead within minutes. Whaling was inherently dangerous work even in sheltered conditions, and the Barents added its own particular hazards on top of the occupational ones. The bowhead whale itself, when struck and still alive, could capsize or destroy a small whaling boat with a single movement of its tail. Add to that the weather, the ice, and the distance from any help, And you have a working environment that killed steadily and without ceremony throughout the entire era. The bowhead population around Svalbard was effectively destroyed within about a century of intensive hunting. By the mid-1700s, the catches had declined so severely that the Svalbard grounds were no longer commercially viable, and the industry moved elsewhere. Smeerenberg was abandoned and eventually collapsed. What remains today is a series of brick foundations, rusted iron tripods, and the graves of men who died there and were buried in the frozen ground. Some from accidents, some from illness, some from what the records describe simply as the cold. The site has been archaeologically studied since the 1970s, and the artifacts and human remains found there have given historians a detailed picture of what life and death at Smeerenberg actually looked like. While the Dutch and English whalers were operating their seasonal industrial settlements, there was another group of people navigating the Barents Sea who left a quieter, but in many ways more durable record. The Pomors were communities of Russian settlers living along the shores of the White Sea and the Kola Peninsula, in places like Arkhangelsk and the villages of the Karelian coast. They had been fishing and trading in the waters of the northern Barents for centuries before any Dutch or English explorer arrived, using routes and knowledge that had been accumulated across generations and passed down through a combination of practical instruction and oral tradition. The Pomors built their own distinctive vessels called kochi, which were designed specifically for Arctic conditions. The hull of a coke was rounded at the bottom in a way that allowed it to be pushed upward by ice pressure rather than crushed, a design principle that later influenced the construction of purpose-built icebreakers. They navigated by stars, by the behaviour of currents and wildlife, by the colour and texture of the ice, and by accumulated knowledge of the sea's seasonal patterns that no written chart could fully capture. They traded with the indigenous Nenets people of Novaya Zemlya and the surrounding coasts, and some Pomor communities maintained regular routes across the Barents to Svalbard that they had used for so long that the archipelago appeared in their records simply as a familiar destination. The Pomors did not leave the kind of detailed written accounts that European explorers produced. Their knowledge was practical and communal rather than documentary. But the losses they suffered were real and regular. The Barents Sea did not make exceptions for experience or local knowledge. A sudden polar low, an unexpected shift in ice conditions, a navigational error in the dark, any of these could take a vessel and its crew without warning, regardless of how many years those men had spent on the water. There are records from Russian Orthodox monasteries along the White Sea coast of masses said for fishermen and traders who went north and did not return, entries that accumulate across the centuries into a quiet, steady toll. What is striking, looking at all of these groups together, is how consistent the pattern is. Barents and his crew, the Dutch whalers of Smeerenberg, the Pomor traders of the White Sea coast. They came from different cultures, with different levels of technology, different types of vessels, and very different relationships to the sea. But the Barents treated them with the same fundamental indifference. The experienced and the inexperienced, the well-equipped and the modestly equipped, the careful and the careless, all encountered the same physical forces. The cold water that kills in minutes, the ice that moves without warning, the storms that develop faster than any messenger can carry news of them, the shallow banks that turn a moderate swell into something that can roll a ship. There is something worth sitting with in the fact that the winter camp of Willem Barents was preserved almost perfectly for nearly 3 centuries, while the names of most of the men who died in Smeerenberg or were lost at sea during the same era were never recorded at all. History has a way of remembering the exceptional and losing the ordinary. But the ordinary losses, the fishing boat that did not come home, the trading vessel last seen heading north in October, the whaling crew whose ship was found drifting empty, these were the texture of life in the communities that depended on the Barents Sea. They were not exceptional events to the people who lived through them. They were simply part of what the sea cost. By the time the 17th century whaling era was winding down, the Barents Sea had already established the character it would maintain through every subsequent era of human activity. productive enough to draw people to it, dangerous enough to kill them regularly, and remote enough that the dying happened largely out of sight. The bowhead whale was gone from Svalbard's waters. The Dutch and English whalers moved on. Smeerenberg fell into the frozen ground, but the sea itself continued, carrying its weather and its ice and its shallow, treacherous banks into the centuries ahead. The Pomors continued their routes for a while longer, though their world was gradually absorbed into the expanding Russian imperial economy. New kinds of ships appeared. New reasons to be in the Barents accumulated. The cod and haddock that had been fished in these waters since medieval times continued to draw fishing fleets north. Russian and Norwegian interests in the region grew more formal, more organised, more industrialised. The sea that Barents had tried to cross in search of a trade route became a place where nations had permanent strategic interests. And then, in the 20th century, those interests became something else entirely. The Barents Sea stopped being primarily a place of commerce and exploration, and became something far more consequential, a theatre of war, and then a theatre of something that was not quite war, but was never quite peace either. The scale of human activity in the sea, and the scale of human loss, was about to increase by an order of magnitude. The whalers and explorers of the earlier centuries had operated in the dozens and hundreds. What was coming would involve thousands of ships, hundreds of thousands of men, and a level of violence that would make even the worst storms of the Barents seem, briefly, like a secondary concern. The first convoy left Iceland in August of 1941. It was a small operation by the standards of what would follow: 6 merchant ships, a modest escort, a route that had never been tested in wartime. The ships were carrying rubber, tin, wool, and a small quantity of military equipment. They arrived in Arkhangelsk without incident. Almost no one outside of a few naval planning offices knew the convoy had happened at all. But that quiet beginning was the opening of something that would, over the next 4 years, become one of the most sustained and costly maritime campaigns in history. Between 1941 and 1945, 78 Allied convoys made the run from Iceland or Scotland to the Soviet ports of Murmansk and Arkhangelsk. Roughly 1,400 merchant ships participated in total, carrying supplies that the Soviet Union desperately needed to sustain its war effort against Germany: tanks, aircraft, fuel, ammunition, food, raw materials, machine tools, and vehicles by the tens of thousands. The route passed through or near the Barents Sea on every run, and the Barents was not simply a backdrop to what happened. It was an active participant. The weather, the ice, the darkness, and the cold were not incidental hazards. They shaped every tactical decision, every loss, every survival. The convoys ran through conditions that are genuinely difficult to describe in a way that does them justice. In winter, the route offered the protection of darkness and the cover of ice, but it also offered temperatures that could freeze spray onto a ship's superstructure faster than crews could chip it away, and seas that could overwhelm a small escort vessel in a matter of hours. In summer, the midnight sun removed the darkness that concealed ships from enemy aircraft, and the retreating ice opened routes that German submarines and bombers could patrol more freely. There was no good season for the Arctic convoys. There were only different kinds of danger. The men who sailed these routes knew what they were sailing into. The merchant sailors were not military personnel in most cases. They were civilian mariners, drawn from Britain, the United States, Norway, and other allied nations, and they had been warned, at least in broad terms, about what the route involved. Many of them had already survived torpedo attacks in the Atlantic. The Arctic convoys added an entirely new layer of threat on top of the ones they already knew. A man who survived a torpedo hit in the Atlantic might have minutes to get into a lifeboat, and reasonable odds of rescue. In the Barents, the water temperature reduced that calculation dramatically. At 0 to 2 degrees Celsius, the kind of temperatures common in the Barents in winter, a man in the water without a proper survival suit would lose the ability to swim within 10 minutes. He would lose consciousness within 30. Rescue had to be almost immediate to be meaningful, and in the chaos of a convoy under attack, immediate rescue was rarely possible. The convoy that has come to define this era, the one that is most remembered and most studied, is Convoy PQ-17. It sailed in late June of 1942 during the period of near-continuous summer daylight. 35 merchant ships escorted by a substantial force of warships. The convoy was carrying supplies on a scale that reflected how critical the Soviet front had become. Nearly 430 tanks, over 200 aircraft, roughly 3,300 vehicles, and enormous quantities of other war materials. By the standards of what was needed, it was still not enough. By the standards of what was about to be lost, it was almost everything. On the 4th of July, 1942, the British Admiralty received intelligence suggesting that the German battleship Tirpitz, along with other heavy surface units, had moved to Norwegian fjords and might be preparing to attack the convoy. The fear was real. The Tirpitz was the largest battleship in the German fleet, and the Allied surface escort was not equipped to fight her. The first Sea Lord, Dudley Pound, made the decision personally. The convoy was to scatter. The merchant ships were ordered to disperse and proceed independently to their destinations. The escort withdrew. The merchant sailors, suddenly alone in the Barents Sea, had no protection against what came next. The Tirpitz never actually attacked. She returned to port without engaging the convoy, but the order to scatter had already been given, and it could not be recalled. The scattered merchant ships, now spread across hundreds of miles of open water, were hunted at leisure by German submarines and Luftwaffe aircraft over the following days. 24 of the 35 ships were sunk. 153 merchant sailors were killed. The cargo that went to the bottom represented a loss that the Soviet military could feel. All of those tanks, aircraft and vehicles gone. The survivors who made it to the Soviet coast arrived shaken in a way that went beyond ordinary combat experience. Some of them had watched ships around them burn and sink for days, unable to help, knowing that the water they were sailing through was the same water in which the men on those ships had died. The decision to scatter PQ-17 has been debated ever since. Some historians have argued it was a catastrophic error, made on the basis of incomplete intelligence. Others have pointed out that the threat from the Tirpitz was real, and that Pound was working with the information he had. What is harder to argue with is the outcome. The scattering of PQ-17 demonstrated something about the Barents that would be confirmed repeatedly. It is not a sea that forgives dispersal. The convoy system worked, in the Barents as elsewhere, because concentration allowed mutual protection. Alone in that water, a merchant ship was simply a target. 5 months after PQ-17, the Barents Sea was the site of a very different kind of engagement. On the 31st of December 1942, a German force that included the heavy cruisers Hipper and Lützow, along with 6 destroyers, moved to intercept convoy JW-51B, which was carrying supplies to Murmansk. The British escort consisted of destroyers and smaller vessels, significantly outgunned by the German ships. What happened over the following hours has become one of the more studied small ship actions of the war, partly because of its tactical interest and partly because of its political consequences. The British destroyers, under Captain Robert Sherbrooke, did something that required a particular kind of nerve. They used smoke, aggressive manoeuvring, and the poor visibility of the Arctic winter to bluff the German cruisers into hesitation. They made the German commanders uncertain about what they were facing. The Hipper damaged Sherbrooke's ship badly enough that he lost the sight in one eye and had to be carried from the bridge, but the convoy was not destroyed. The Germans eventually withdrew without sinking a single merchant ship. Sherbrooke was awarded the Victoria Cross. The aftermath in Berlin was, by multiple accounts, spectacular in the worst way. Adolf Hitler, who had expected the German surface fleet to destroy the convoy decisively, was told instead that his heavy cruisers had been driven off by British destroyers. His rage at the German Navy's leadership was significant enough that Grand Admiral Raeder resigned shortly afterward, replaced by Karl Dönitz. Hitler reportedly threatened to decommission the entire surface fleet and melt down its ships for steel. The Battle of the Barents Sea, as it came to be known, did not change the course of the war, but it illustrated something about the sea itself. The conditions that made it so deadly also made it deeply unpredictable as a military environment. The darkness, the weather, the limited visibility, the cold that affected men and equipment alike, these did not favour either side. They simply punished everyone. What is worth understanding about the convoy era, if you try to hold it all in mind at once, is the sheer accumulation of threat that the men on those ships were navigating. It was not simply the German Navy. It was not simply the weather. It was all of it simultaneously, with no reliable way to predict which danger would come first or from which direction. A convoy might pass through a storm severe enough to scatter ships and damage equipment, and then emerge into clearer weather directly into a submarine patrol line. Aircraft could appear from Norwegian bases with little warning. Ice could force a convoy south into waters where German submarines were waiting. The cold that froze spray onto superstructures also degraded the performance of weapons and machinery, slowed the hands of men trying to work on deck, and shortened the survival time of anyone who went into the water. The crews of the escort vessels had it differently from the merchant sailors, though not necessarily better. The destroyers and corvettes that accompanied the convoys were small ships by naval standards, and the Barents Sea treated them accordingly. Waves that a larger vessel might ride out could put a destroyer's bow underwater. Ice accumulation on a small warship was not just uncomfortable. It raised the centre of gravity and reduced stability in a way that could become genuinely dangerous. The men who served on those ships spent weeks at a time in conditions that made ordinary shipboard life feel like a memory from another world. The Arctic convoys delivered in total approximately 4 million tons of supplies to the Soviet Union over the course of the war. The losses were significant. Roughly 100 merchant ships sunk, along with 18 warships. But the convoys ran. They ran through the worst the Barents Sea could produce, and through the worst the German military could organise against them, and they kept running until the war ended. The men who survived them came home with a particular kind of knowledge, what it felt like to be cold in a way that does not fully leave you, what it felt like to watch a ship burn on a dark horizon and know there was nothing to be done, what it felt like to be in a place where the sea itself was not neutral. For a long time after the war, the Arctic convoys received less recognition than many felt they deserved. The Soviet government was not particularly interested in acknowledging the scale of Western material support it had received. The British and American governments had other stories to tell. The merchant sailors, who were civilians rather than military, were not always included in the formal commemorations that servicemen received. It took decades for medals to be formally awarded to many of the surviving veterans. By the time the recognition came, a great many of the men who had earned it were gone. The wrecks of that era are still in the Barents. Some of them are in water shallow enough that they have been located and documented. Others are in depths that make them difficult to reach. The cargo that went down with PQ-17's ships is still there, somewhere on the seafloor. Tanks and aircraft and vehicles that never reached the Soviet front, preserved in the cold and dark. There is something quietly strange about that. The war ended. The Soviet Union rose and fell. The political world that those convoys were trying to sustain has changed beyond recognition. But the ships are still where they sank, and the water around them is still the same water, still cold, still capable of producing the same storms, still indifferent to everything that has happened since. The Barents Sea did not pause after 1945 to reflect on what had occurred within it. The war ended, and the convoys stopped, and the sea continued as it had always continued. But the nations that bordered it did not simply return to fishing and trade. The strategic importance of the Barents, which the war had made undeniable, did not diminish with peace. If anything, it intensified. The Soviet Union, now in possession of nuclear weapons and in direct confrontation with the Western powers, understood the Barents Sea as something it had perhaps always been, but was now more explicitly a boundary, a buffer. a place from which the most consequential weapons ever built could be deployed. The fishing boats and merchant vessels that had historically defined human activity in these waters were about to share them with something very different. Beneath the surface of the same sea where convoy sailors had frozen and drowned, a new kind of presence was taking shape, quiet and enormous and armed in ways that made the warships of the Second World War look almost modest by comparison. The Soviet Northern Fleet made its home at Severomorsk, a closed city on the Kola Peninsula, roughly 30 kilometers northeast of Murmansk. If you look at a map, the location makes immediate sense. The Kola Peninsula juts northward into the Barents Sea, and Severomorsk sits on the eastern shore of the Kola Fjord, sheltered enough for a large naval base, but close enough to open water that submarines could slip out into the Barents within hours of leaving port. The base was not a secret exactly. Western intelligence knew it existed, but the full scale of what the Soviet Union was building there through the 1950s and 1960s took years to become clear, and by the time it did, the Northern Fleet had grown into the largest concentration of naval power in Soviet history. At its peak, the Northern Fleet operated more than 100 submarines, many of them nuclear-armed. The Barents Sea became their primary operating ground. Submarines would leave Severomorsk, pass through the Barents, and either conduct patrols beneath the Arctic ice cap or transit south through the Norwegian Sea toward the Atlantic. The patrols were long and demanding. Crews spent weeks and sometimes months submerged, running drills, maintaining systems, waiting. The submarines carried ballistic missiles capable of reaching American cities. The Americans and their NATO allies knew this, and their own submarines and aircraft spent considerable effort tracking the Soviet boats, trailing them, mapping their patrol patterns. The Barents Sea, which had just spent 4 years as a battlefield for convoy sailors and German U-boats, was now the central arena of a different kind of confrontation. Quieter, but in some ways more consequential. The technology was new, the stakes were new, but the sea was the same, and it continued to behave as it always had. The Soviet submarine program, for all its ambition and scale, suffered from problems that were never fully resolved. Some of these were problems of design. Others were problems of materials or of manufacturing quality, or of the pace at which the Soviet military demanded new vessels be produced. Nuclear reactors are not forgiving of shortcuts, and submarines that operate at depth in cold water leave very little margin for error. The result was a series of accidents that, taken together, constitute one of the less discussed maritime disaster records of the 20th century. The K-19 is usually where these stories begin. She was a hotel-class ballistic missile submarine, the first Soviet nuclear submarine to carry ballistic missiles, and she was commissioned in 1961 with a degree of haste that her crew would come to feel very personally. In July of that year, while operating in the North Atlantic near the boundary with the Barents, her reactor cooling system developed a leak. The primary coolant circuit lost pressure, and the reactor temperature began to rise toward levels that could cause a meltdown. There was no backup cooling system. The captain, Nikolai Zateyev, made the decision to have his engineers improvise one, cutting into other ship systems and fabricating a jury-rigged connection that might bring water to the reactor. The men who did this work received lethal doses of radiation. 8 of them died within weeks. The rest of the crew suffered varying degrees of radiation exposure that affected their health for the rest of their lives. The K-19 was saved from a full meltdown, but the human cost was enormous, and the Soviet government classified the incident for decades. The crew who survived were told not to speak of it. The men who died were buried quietly. It was not until the Soviet Union collapsed that the full story became publicly known. The K-19 was not a Barents Sea incident in the strictest geographic sense, but she was a Barents Sea submarine, built for Barents operations, crewed by men from the Northern Fleet. And her story was not unusual in its broad shape. Through the 1960s and 1970s, Soviet nuclear submarines experienced reactor accidents, fires, flooding, and equipment failures at a rate that, had it been publicly known at the time, would have alarmed anyone who understood what these vessels were carrying. The Soviet Navy did not publicize these events. The losses were absorbed into the classified record and the program continued. The K-278 Komsomolets is a different kind of story, and it is one that belongs more directly to the waters near the Barents. She was a Mike-class submarine, the only one of her kind ever built, and she was in some ways genuinely remarkable. Her hull was constructed from titanium, which gave her a diving depth capability far beyond any other submarine in the world at the time. She could descend to more than 1,000 meters, deep enough to be essentially unreachable by any contemporary anti-submarine weapon. She was fast, she was deep diving, and she represented a significant Soviet engineering achievement. On the 3rd of April 1989, she was on patrol in the Norwegian Sea, south and west of the Barents proper, when a fire broke out in one of her aft compartments. Fires on submarines are among the most feared emergencies in naval operations. There is no way to simply open a door and let the smoke out. The air is shared, the space is confined, and the systems that keep the vessel functioning are all connected. On the Komsomolets, the fire spread faster than the crew could contain it. The submarine surfaced, but the fire continued to burn through critical systems. She sank in about an hour and a half, going down in water roughly 1,680 meters deep. Of the 69 men aboard, 42 died, some in the fire, some in the water afterward. The sea temperature was around 2 degrees Celsius. The rescue response was slow. Survival suits were not adequate. Men who made it into the water did not survive long enough for help to arrive. The Komsomolets came to rest on the seafloor with 2 nuclear warheads in her torpedo tubes. She's still there. She's been there for more than 35 years. Norwegian and Russian scientific teams have periodically returned to monitor the wreck, because there is genuine concern about what the sea is doing to those warheads and to the submarine's reactor over time. In 2019, a Norwegian monitoring expedition detected elevated levels of radioactive cesium in water samples taken directly from ventilation openings in the hull, levels that were, according to the researchers, about 800,000 times higher than normal seawater concentrations, though still considered low in absolute terms and not an immediate public health threat. The wreck is not leaking in a catastrophic way, but it is not sealed, and it is not stable, and it will not become more stable as the years pass. The Komsomolets is a slow question, sitting in the dark at the bottom of a cold sea, and nobody has a fully satisfying answer to it yet. These incidents were not isolated. They were part of a pattern that the Cold War produced in the Barents and the waters around it. The Soviet Navy lost submarines in 1968, in 1970, in 1983, in 1986. Some of these losses were in the Pacific, some were in the Atlantic. But the Northern Fleet, operating out of the Kola Peninsula and into the Barents, contributed its share. The American Navy had its own accidents, though fewer in number. The USS Thresher sank in 1963 during deep diving trials, and the USS Scorpion was lost in 1968, both with all hands, both in the Atlantic. The Cold War beneath the surface was not bloodless. It simply bled quietly, in places where the public was not watching. What made the Barents particularly consequential in this context was not just the number of Soviet submarines operating there, but what those submarines represented strategically. The Barents was the primary transit route for Soviet ballistic missile submarines heading toward their patrol areas in the Arctic Ocean, from which they could strike targets in North America. NATO's response was to establish a network of surveillance, using underwater hydrophone arrays, patrol aircraft, and attack submarines to track Soviet movements through what became known as the GIUK Gap, the stretch of ocean between Greenland, Iceland, and the United Kingdom that Soviet submarines had to cross to reach the Atlantic. The Barents was the starting point for all of this. It was where the submarines began their journeys, and where they returned, and where, if a conflict had ever escalated to the point of actual hostilities, the first engagements would almost certainly have taken place. The scale of nuclear material that accumulated in and around the Barents during this period is genuinely difficult to hold in mind. Reactors operating on submarines that were later decommissioned and improperly stored, reactors from submarines that sank, solid radioactive waste dumped directly into the Kara Sea just east of Novaya Zemlya by the Soviet Navy over several decades, a practice that included dumping entire reactor assemblies, some still containing fuel. The full extent of this dumping was not acknowledged until after the Soviet Union's collapse, when Russian environmental scientists and journalists began to piece together the record. The International Atomic Energy Agency conducted assessments in the 1990s and concluded that while the dumped material posed a long-term monitoring concern, the immediate risk to human populations was low. That assessment has been periodically revisited as monitoring technology has improved. There is something worth sitting with here. The Barents Sea, which had already accumulated the wrecks of 17th century whaling ships, the hulls of convoy vessels from the Second World War, the bones of men who had died in every possible way a cold sea can kill a person, was now also the keeper of nuclear material from a superpower confrontation that the world had spent 50 years hoping would never fully ignite. The sea did not choose any of this. It simply received what was placed in it, or what sank into it, and held it in the cold and the dark as it holds everything. The Soviet Northern Fleet began to decline after the Cold War ended. The Russian Navy that inherited it in 1991 faced budget cuts so severe that many submarines could not be maintained, could not be fueled, could not be crewed. Vessels that had been operational for decades sat in harbours at the Kola Peninsula, slowly deteriorating. The decommissioning process for nuclear submarines is complicated and expensive, and Russia in the 1990s had neither the money nor, at times, the institutional capacity to do it properly. Some submarines were eventually dismantled with international assistance, particularly from the United States under the Nunluga Cooperative Threat Reduction Program, which helped fund the safe disposal of former Soviet nuclear weapons and delivery systems. Others waited in various states of decay. The environmental situation at the Kola Peninsula in the 1990s was, by most accounts, genuinely alarming to anyone who looked at it carefully. But the Russian Navy did not disappear. It contracted, it struggled, and it slowly began to rebuild. By the early 2000s, Russian military spending was increasing again, and the Northern Fleet was beginning to recover some of its former operational capacity. New submarine classes were being commissioned, patrols were resuming. The Barents Sea was returning to something closer to its Cold War role as a primary operating area for Russian strategic forces. And it was in this context, during a period when the Russian Navy was trying to demonstrate its recovery and its capabilities, that the Barents Sea produced the disaster that most people associate with it when they hear the name. Not a convoy scattered by German aircraft, not a submarine lost in a reactor accident during the classified decades of the Cold War. Something that happened in full view, in peacetime, in the summer of 2000, watched by the world in real time, and made worse by every hour that passed without rescue. The Kursk was out on exercises. She was a large, powerful, modern submarine, and the Navy was proud of her. What happened next would take everything that the Barents Sea had been accumulating across centuries of human tragedy, all of its cold indifference, all of its distance from help, all of its capacity to make the gap between catastrophe and rescue feel impossibly wide, and concentrate it into a few terrible days in August. The K-141 Kursk was commissioned in 1994, and by the standards of the Russian Navy at that time, she was genuinely impressive. An Oscar II-class cruise missile submarine, one of the largest attack submarines ever built, she measured 154 meters from bow to stern, roughly the length of 1.5 American football fields. Her displacement when submerged was around 24,000 tons. She carried 24 P-700 Granite cruise missiles in launch tubes angled outward from her hull, each one capable of carrying a nuclear warhead, and she was designed to hunt and destroy NATO carrier battle groups. She had a crew of 118 officers and sailors, and on this particular exercise in August 2000, she was carrying an additional 37 personnel, including weapons specialists and observers. The total number aboard was 118. Some accounts say 118, some say 118 plus additional personnel depending on the source, but what is consistent across all records is that she carried 118 men when she went down. That number matters. It becomes important very quickly. The Northern Fleet's summer exercises in August 2000 were, in some ways, a statement of intent. Russia had been through a decade of severe military decline. The 1990s had been genuinely humiliating for the Russian armed forces in ways that the public had not always fully understood. Ships rusting in harbour, sailors going unpaid for months, nuclear submarines sitting with their reactors improperly maintained because there was no money to do the work properly. The exercises that August were meant to signal something different, a recovering fleet, a capable navy. President Putin, newly elected, had staked part of his early political identity on restoring Russian military prestige, and the Northern Fleet exercises were one of the first large demonstrations of that ambition. The Kursk was one of the centerpieces. She was scheduled to conduct a simulated attack on surface ships using practice torpedoes. On the morning of August 12, 2000, the Kursk was operating in the Barents Sea at a depth of around 100 meters, roughly 135 kilometers from the naval base at Severomorsk. At approximately 11:28 in the morning, something went wrong in the torpedo room at the bow of the submarine. The weapon involved was a practice torpedo, designation 65-76A, and it was powered by a fuel called high-test peroxide, or HTP, which is a highly concentrated form of hydrogen peroxide. HTP had been in use as a torpedo propellant since the 1950s, and it had a known problem. It is extraordinarily unstable. When it comes into contact with almost any contaminant, including rust, organic material, or certain metals, it decomposes rapidly and releases enormous heat. The torpedo that failed on the Kursk had a defective weld in one of its fuel components. HTP leaked through that weld, came into contact with the torpedo casing, and the reaction was immediate. The first explosion was recorded by seismographs in Norway at 11:28:26. It was relatively small in submarine terms, roughly equivalent to 100 to 250 kilograms of TNT, but in an enclosed space it was enough to blow open the torpedo room and kill the men working there instantly. What happened 135 seconds later was the event that made the Kursk impossible to survive for most of the crew. The heat from the first explosion cooked off multiple warheads in the torpedo room simultaneously. Seismographs registered a second explosion at 11:30:42, and this one was not small. Estimates of its force range from 3 to 7 tons of TNT equivalent. Norwegian seismic stations recorded it as a magnitude 3.5 earthquake. The explosion tore through the forward compartments of the submarine with a force that was, by the physical evidence recovered later, almost incomprehensible. The first 4 compartments were essentially destroyed. The blast doors between compartments, designed to contain exactly this kind of catastrophic event, held in some places and failed in others. The submarine hit the seafloor at a depth of about 108 meters, nose down, at a shallow angle, and came to rest with her bow section devastated and her aft section largely intact. And this is where the story of the Kursk becomes something different from a simple mechanical disaster. Because 23 men were still alive, they had made it to the 9th compartment, the aft reactor and turbine section, which was the farthest from the explosion and the most structurally sound. Captain Lieutenant Dmitry Kolesnikov, who was 27 years old, wrote a note. The note was found when the submarine was eventually raised, and it is one of the most quietly devastating documents to come out of any maritime disaster. He wrote it in the dark because the emergency lighting had failed. He described the situation clearly and without apparent panic. He listed the names of the 23 men who had survived the initial explosions and reached the compartment. He noted the time, 13:15, about an hour and 45 minutes after the second explosion. He wrote that they could not reach the surface because of the pressure differential at the hatch. He wrote that he was writing in complete darkness. The note ends. It is not dramatic in its language. It is just a man documenting what is happening clearly and carefully in the last hours of his life for whoever might eventually find it. The men in the ninth compartment had oxygen regeneration cartridges, which are chemical canisters that produce oxygen when they come into contact with water. At some point, one of these cartridges was dropped into seawater that had flooded into the compartment. The resulting chemical reaction caused a fire and a pressure surge that would have been fatal within seconds. The exact sequence of events in the aft compartment during those hours is not fully known, but the forensic analysis conducted after the submarine was raised suggested that the men there survived for somewhere between 3 and 8 hours after the initial explosions. The rescue response is the part of the Kursk story that people who followed it at the time remember with a particular kind of grief, because it was not the sea that failed those 23 men in the aft compartment. It was everything that came after. The Russian Navy initially did not acknowledge that anything had gone wrong. There was a delay of many hours before the distress signal was officially recognized as a genuine emergency rather than a communication failure. When the rescue operation was finally organized, it relied on Russian deep-sea rescue vehicles, specifically the AS-34 mini-submarine, which attempted to reach the Kursk's escape hatch on the stern. The AS-34 made multiple dives over 2 days. Each attempt failed. The rescue vehicle could not achieve a proper seal with the hatch. Explanations offered afterward included damage to the hatch, combing from the explosion, the angle at which the submarine was resting, and the deteriorated mechanical condition of the rescue vehicle itself. Some accounts from the rescue crews described equipment that was simply not functioning as it should have been, which was, in the context of a decade of naval underfunding, not entirely surprising, but no less terrible for that. Norway and the United Kingdom both offered assistance within the first day. Norway had a rescue vessel, the Normand Pioneer, and a team of divers with experience in exactly this kind of operation. Britain offered a similar capability. The Russian government declined these offers for several days, citing concerns about classified equipment aboard the Kursk and, by most analyses, a degree of institutional reluctance to admit that the Russian Navy could not manage the rescue on its own. By the time the Norwegian divers were permitted to attempt access, on August 21st, 9 days after the sinking, it took them approximately 4 hours to open the hatch that the Russian rescue vehicles had been unable to open for days. The compartment was flooded. There was no one left to save. The Norwegian diver who opened the hatch, a man named Willy Östrom, later described the moment simply. He opened it, and the compartment was full of water. That was the end of the rescue operation. The Russian government's handling of the Kursk disaster became a major political crisis. President Putin remained on vacation at a Black Sea resort for several days after the sinking became public. The state-controlled media was slow and inconsistent in its coverage. Families of the crew who gathered at the naval base in Severomorsk were given contradictory information. At one point, a naval official told a distraught mother that the crew was still alive and efforts were ongoing, at a time when the Navy had already concluded internally that survival was essentially impossible. A video of that moment circulated widely and became one of the defining images of the disaster's aftermath. The anger of the families and of the Russian public was real and significant. What the recovery operation revealed when the Kursk was eventually raised in the autumn of 2001 was a picture of a submarine in a specific kind of condition that told a story about the state of the Russian Navy in the years leading up to the disaster. The torpedo that had failed was using fuel that many experts had long considered unsafe. The British and American navies had phased out HTP propellant in the 1950s and 1960s precisely because of its instability. The Russian Navy had continued using it. The well that had failed on the torpedo was later identified as substandard, and the maintenance records for the weapon were, according to the official investigation, inadequate. None of this was the fault of the 118 men aboard the Kursk. It was the accumulated consequence of a decade of underfunding, deteriorating maintenance culture, and institutional pressure to demonstrate capability with equipment that was not fully ready to demonstrate it. The Barents Sea held the Kursk for just over a year. The raising operation, conducted in 2001 by a Dutch salvage company called Mamoe, in collaboration with Hirama Marine Contractors, was one of the most technically complex submarine salvage operations ever attempted. The bow section, which had been almost completely destroyed by the second explosion, was cut off and left on the sea floor. The remaining hull was lifted using a system of 26 hydraulic cables attached to a purpose-built lifting frame, transferred to a pontoon, and towed to a dry dock at Roslyakovo. The operation took months of planning and was executed in a single lift. When the hull was finally brought up and into dry dock, and when investigators were able to examine what was inside, the findings confirmed what the seismic data and the physical evidence had already suggested. The forward compartments had been destroyed by an explosion of enormous force. The aft compartments were intact, and in the 9th compartment they found the 23 men, and they found Kolesnikov's note. The official Russian investigation concluded that the disaster was caused by the torpedo fuel leak. A separate investigation conducted by Russian prosecutors reached similar conclusions. There were criminal proceedings, but they did not result in convictions. The families of the crew received compensation from the Russian government. A memorial was constructed. The Kursk's conning tower, which had been removed from the hull during the salvage, was placed at a memorial site in Murmansk. It stands there now. What the Kursk disaster did, beyond the immediate tragedy and the political fallout, was force a confrontation with something that the Russian Navy and the Russian government had been managing quietly for years: the gap between the image of capability and the reality of condition. The submarines of the Northern Fleet had, through the 1990s, been presented publicly as formidable, capable, and combat-ready. The Kursk was supposed to be one of the best of them, and she was in many ways an impressive vessel, but impressive vessels require maintenance, and maintenance requires money, and the Russian Navy in the 1990s had not had enough of either. The Barents Sea, which does not make allowances for institutional problems or budget shortfalls or political optics, simply presented the consequences of all of that in one catastrophic morning in August. There is something about the Kursk that makes it different from the other disasters the Barents Sea holds. The convoy losses of the Second World War were enormous in scale, but they happened in a context where catastrophic loss was, in a terrible way, expected. The Cold War submarine accidents were hidden, classified, managed out of public view. The Kursk happened in peacetime during an exercise, in a sea where the weather that August was relatively calm. The sea itself was not particularly violent that day. The water temperature, the wave conditions, the visibility, none of these were the primary factors. The Barents Sea did what it always does. It simply received the submarine when she sank, held her at 108 meters, and waited. The failure was human, institutional, mechanical, and political, and the sea had no opinion about any of it. The depth at which the Kursk rested, 108 meters, was not extreme. In better circumstances, with functional equipment and a faster response, a rescue might have been possible. That is the part that is hardest to let go of. Not the explosion, which was catastrophic and fast, but the hours afterward. The 23 men who made it to the 9th compartment. The note written in the dark. The hatch that a Norwegian diver opened in 4 hours after the Russian rescue vehicles had failed for 9 days to do the same thing. The Barents Sea has held many things that the world would prefer to forget, but the Kursk is not one of the forgotten ones. It remains the most visible, the most documented, the most politically charged maritime disaster the sea has produced in the modern era. And it is, in a way, the clearest demonstration of what the Barents has always represented. A place where the margin for error is extremely small, where the distance from help is enormous, and where the consequences of failure arrive quickly and completely. The military dimension of the Barents Sea did not end with the Kursk. The Russian Navy rebuilt, slowly and then more quickly. New submarines were commissioned, new exercises were conducted. The strategic importance of the sea, its role as the primary operating area for Russia's submarine-based nuclear deterrent, did not diminish. If anything, as Russia's relationship with NATO became more complicated in the years after 2000, the Barents Sea returned to something resembling its Cold War significance. Russian submarine activity in the North Atlantic increased. NATO surveillance operations intensified in response. The sea became, once again, a place where the world's largest military powers were watching each other carefully across the cold water. But alongside all of that, beneath all of that strategic calculation, the Barents Sea was also something else entirely. It was a fishery, one of the most productive in the world, and the people who worked it, the trawlermen and the deckhands and the skippers of small vessels operating in those same waters where nuclear submarines ran their patrols, they were encountering a different version of the sea's indifference. Not the dramatic world historical kind, the quieter kind, the kind that does not make the news or does not stay in the news for long, because the losses are smaller and the victims are not sailors in uniform but fishermen doing their jobs in conditions that are, by any reasonable measure, extraordinarily dangerous. That story, the one the fishing industry knows, is the one the Barents Sea tells most consistently, year after year, in waters that are among the richest and the most unforgiving on Earth. The Barents Sea fishing industry is, by the numbers, one of the most significant in the world. The waters above the shallow banks, the same banks that make the sea so geographically treacherous, are extraordinarily productive. Cold, nutrient-rich water, upwelling from the sea floor, supports massive populations of cod, haddock, capelin and snow crab. The Northeast Arctic cod stock, which is shared between Norway and Russia and managed under a bilateral agreement that has, remarkably, survived decades of political tension, is the largest wild cod stock on Earth. In a good year, the total allowable catch for that stock alone runs to around 900,000 tonnes. Norwegian and Russian fleets dominate the fishery, but vessels from other nations work these waters too. There are processing ships, factory trawlers, small coastal vessels and large deep-sea trawlers. At any given time, particularly in the spring and autumn fishing seasons, there can be hundreds of vessels operating across the Barents simultaneously. For the people on those vessels, the sea is not an abstraction. It is not a strategic asset or a geopolitical arena. It is the place where they go to work, and it is a workplace that has been killing people, quietly and persistently, for as long as people have been fishing there. The specific dangers that face fishing vessels in the Barents are worth understanding in some detail, because they are different in character from the dangers that face the warships and submarines of earlier sections of this story. They are not the result of enemy action or catastrophic mechanical failure in a billion-dollar vessel. They tend to be more ordinary in their origins, and that ordinariness is part of what makes them so persistent. Spray icing is one of the most significant. When air temperatures drop below roughly -8 degrees Celsius and wind speeds are high, seawater spray freezes almost immediately on contact with any surface. On a trawler at sea in winter, this means that ice accumulates on the hull, the superstructure, the rigging, the fishing gear, the deck equipment, everything exposed to the air. It accumulates quickly. In severe conditions, a vessel can gain several tons of topside weight within a matter of hours. The problem with that is stability. A fishing vessel is already working with a relatively high centre of gravity when its holds are full and its gear is deployed. Add several tons of ice to the upper parts of the ship, and that centre of gravity rises further. The vessel becomes less stable, in beam seas meaning waves striking from the side rather than head-on or stern-on. A less stable vessel rolls more deeply. And in the Barents in winter, beam seas are not unusual. They are common. Crews can fight icing by going out on deck with mallets and steam hoses and physically breaking the ice away. This is exhausting, cold and dangerous work. People have been swept overboard doing it. and in the worst conditions the rate at which ice accumulates can exceed the rate at which a small crew can remove it. When that balance tips, the outcome can be rapid. There are accounts of vessels in the Barents and the Norwegian Sea capsizing within minutes once the icing became severe enough to critically compromise their stability. The sea does not give much warning, and it does not wait. Gear entanglement is another persistent cause of loss. Trawl nets are large, heavy, and designed to catch things. When they snag on the sea floor, on a wreck, on a rock formation, or on another vessel's gear, the tension on the towing warps can become enormous. In some cases, a snagged net has pulled a vessel's stern down far enough to cause flooding. In other cases, the sudden shock load when a trawl wire parts has injured or killed crew members on deck. The Barents Sea floor, with its banks and ridges and the hundreds of wrecks from the war years, offers no shortage of things for nets to catch on. Engine failure in remote locations is, in any sea, a serious problem. In the Barents, it can be a fatal one. A vessel without propulsion in deteriorating weather, far from port and far from other ships, has very limited options. The sea does not remain calm while rescue is organised, and in winter, the combination of cold air, cold water, and the speed at which conditions can change means that the window between engine failure and irretrievable catastrophe can be very short. The Soviet and Russian trawler fleet operating out of Murmansk has suffered some of the heaviest losses. During the Soviet era, the Murmansk fishing fleet was vast. At its peak in the 1970s and 1980s, the Soviet fishing industry was the largest in the world by tonnage caught, and the northern basin, which encompasses the Barents, was one of its primary operating areas. The fleet included large factory trawlers that could stay at sea for months, as well as smaller vessels working closer to shore. The losses across that era were significant, but they were not always well documented publicly. Soviet maritime accident reporting was not transparent. Losses were sometimes acknowledged, sometimes not. What we do know is that the sea took a steady toll year after year on vessels and on the men who worked them. In the post-Soviet period, as the Russian fishing industry went through a difficult restructuring, the situation in some respects became worse before it became better. Vessels that had not been properly maintained during the financially chaotic 1990s were still operating. Equipment was aging. Crews were sometimes working on vessels that should have been retired. The combination of an unforgiving sea and an industry under severe economic stress produced predictable results. One loss that drew significant attention, though it occurred not in the Barents but in the Sea of Okhotsk in the Russian Far East, was the sinking of the factory trawler Dalny Vostok in April 2015. 56 people died when the vessel sank rapidly, possibly due to shifting catch weight affecting stability. The accident prompted renewed discussion in Russia about safety standards in the fishing industry, about the age of vessels, about the adequacy of survival equipment, and about the culture of risk acceptance that can develop in industries where the pressure to keep fishing is constant and the pressure to stop and check equipment is less immediate. The Barents fleet was part of that conversation because many of the same structural problems existed there. Norwegian fishing vessel losses in the Barents have followed a different pattern, shaped by a different regulatory environment and a different economic context. But the sea itself makes no distinction between flags. Norwegian trawlers and coastal fishing vessels have been lost in the Barents over the decades, sometimes in conditions that were forecast and known to be dangerous, sometimes in weather that developed faster than expected. The Norwegian Maritime Authority maintains records of maritime accidents, and the pattern in those records is consistent. Fishing vessels are disproportionately represented in maritime fatalities relative to their economic contribution, because the work involves exposure to conditions that other maritime industries largely avoid. There is a particular quality to the losses the fishing industry absorbs that is worth sitting with for a moment. When a warship or a submarine is lost, it tends to generate official investigation, political attention, and historical memory. The names of the vessels, and in many cases the names of the crew, become part of a documented record. When a trawler goes down, the documentation is there, but the public memory is shorter. A trawler sinking in the Barents in January, in conditions that were severe but not unprecedented, with a crew of perhaps 12 or 15 men, generates local news, a maritime accident report, possibly a change in regulation or guidance, and then it recedes. The families of the crew do not recede, of course, but the broader public memory does. This is not a criticism of how these losses are covered. It is simply an observation about scale and attention. The Barents Sea has, over the centuries, taken far more lives through the steady, unglamorous attrition of the fishing industry than through any single spectacular disaster. The convoys, the submarines, the Kursk, these are the events that appear in history books and documentary films, but the trawlermen who went out in November and did not come back year after year, across generations, they are the sea's most consistent cost. The fishing communities of northern Norway, of the Kola Peninsula, of the coastal towns that have sent men out into the Barents for centuries, carry this knowledge in a way that is hard to articulate from the outside. It is not dramatic knowledge. It is more like a chronic awareness, something that sits in the background of daily life in those places. The sea is where the work is, and the work is dangerous, and some years the sea takes someone, and the community absorbs it and continues. That is a very old relationship, and it has not fundamentally changed, even as the vessels have become larger and better equipped, and the forecasting has improved. What has changed is the specific character of some of the risks. The retreat of sea ice in the Barents, driven by the warming that has made this one of the fastest changing marine environments on the planet, has opened new fishing grounds that were previously inaccessible for much of the year. Snow crab, which arrived in the Barents from the North Pacific, possibly as larvae in ballast water, established itself so successfully that it has become a commercially significant species. Vessels now fish in areas and at times of year that were not part of the traditional fishing calendar. New grounds mean new hazards, new bottom topography to learn, new weather patterns in areas where operational experience is limited. The sea is, in a sense, offering new territory, and new territory in the Barents comes with the same fundamental terms as the old territory. There is also the question of what happens when things go wrong in those more remote areas. A vessel in distress close to Tromsø or Hammerfest is in a very different situation from a vessel in distress near the northern banks, far from the Norwegian coast and far from any other ship. The fishing grounds have expanded northward and eastward. The rescue infrastructure has not expanded at the same pace. The helicopter range from the nearest Norwegian base, the response time from the nearest Coast Guard vessel. These are not abstract numbers for a crew in the water in February. They are the difference between survival and not. The specific vulnerability of fishing vessels to capsize in beam seas deserves one more note, because it is the mechanism behind a disproportionate number of losses and it is not always well understood outside the industry. A vessel running before the sea, meaning with the waves coming from behind or heading into the sea, with waves coming from ahead, is in a more controllable situation than a vessel caught broadside to the waves. Fishing vessels often have limited ability to choose their orientation relative to the sea. When gear is deployed, when hauling is underway, when the vessel is holding position over a particular piece of ground, the skipper cannot always simply turn and run. The vessel is committed to a heading, and if the sea builds from a direction that puts the vessel beam on to significant waves, the risk of a serious roll, or of a roll that does not recover, increases substantially. In the Barents, where the weather can shift direction as well as intensity, this is not a theoretical scenario. It is something that skippers think about and manage, and sometimes cannot avoid. The record of the Barents Sea fishing industry is in the end a record of human persistence in a place that does not encourage persistence. The fish are there, in enormous numbers, and they have always been there, and people have always gone to get them, and the sea has always extracted its portion of the cost. That transaction has not been renegotiated by better technology, or better forecasting, or better regulation. though all of those things have reduced the cost at the margins. The fundamental terms remain what they were when Dutch whalers first worked these waters in the 17th century. The sea will give what it gives, and it will take what it takes, and the people who go there accept that at some level, even if they do not always say it plainly. And beyond the fishing grounds, beyond the question of what the sea costs the industry that harvests it, there is the question of the sea itself. What it is physically, what it does meteorologically, how it generates the conditions that make all of these losses possible. The storms that cross the Barents are not random. They follow patterns, they have mechanics, they can be understood. Understanding them does not make them less dangerous, but it does make them less mysterious. And in a sea where mystery has sometimes been confused with unpredictability, that distinction matters. The weather that the Barents produces is, in some respects, among the most extreme and the most difficult to forecast of any maritime environment in the Northern Hemisphere. And the reasons for that are specific, and they are worth examining carefully. The storms that form over the Barents Sea are not simply large versions of the weather systems that cross the North Atlantic. They are a different category of phenomenon, and understanding what makes them different requires spending a little time with the meteorology, because the mechanics are genuinely interesting, and they explain a great deal about why the Barents has the reputation it does. The most significant and the most dangerous weather feature specific to this part of the Arctic is something called a polar low. The name sounds almost bureaucratic, which is misleading, because polar lows are among the most intense small-scale storm systems that form anywhere in the Northern Hemisphere. They are compact cyclones, typically between 200 and 1,000 kilometers in diameter, which puts them considerably smaller than the broad mid-latitude depressions that meteorologists track across the Atlantic. But what they lack in size, they compensate for in speed and severity. A polar low can develop from relatively calm conditions to a full storm within 12 to 24 hours. In some documented cases, the development has been even faster than that. They form most often over the open water of the Barents Sea during late autumn and winter, when cold Arctic air from the north and east moves out over the relatively warmer ocean surface. The temperature difference between the air and the water surface is the engine. Cold, dry air descends over the ocean, picks up heat and moisture, and under the right conditions of atmospheric instability, it begins to rotate. The system intensifies as it feeds on the heat flux from the water below. Wind speeds in a mature polar low can exceed 30 meters per second, which is roughly equivalent to 108 kilometers per hour. That is well into the range of what would be classified as a violent storm on the Beaufort scale, and it arrives with very little warning. The forecasting problem is real, and it is not simply a matter of needing better technology. Polar lows are difficult to predict even with modern satellite imagery, numerical weather models, and dedicated Arctic meteorological monitoring. The reasons are partly physical and partly a matter of data. The Barents Sea is a large, remote body of water with relatively few surface observation points. Weather buoys exist, but their coverage is not dense. Ships in the region provide weather reports when they are there, but large areas of the Barents see relatively little commercial traffic compared to the North Atlantic shipping lanes, and the data density that models need to produce accurate short-range forecasts is simply not always available. Satellite imagery has improved the detection of developing polar lows considerably since the 1980s, but detection is not the same as accurate intensity forecasting. A polar low can be identified on satellite imagery, while still being underestimated in terms of how quickly it will deepen or how strong it will become. For a vessel at sea in the Barents, this creates a specific problem. The standard approach to storm avoidance in open ocean sailing is to monitor forecasts, identify developing systems, and alter course or seek shelter before conditions deteriorate. That approach depends on having enough warning time to act. When a storm can develop from a manageable situation to a dangerous one in 12 hours, and when the forecast for that storm carries significant uncertainty, even 12 hours out, the margin for decision-making narrows considerably. A skipper who receives a forecast at 6 in the morning showing deteriorating conditions might have until the early afternoon to make a decision about where to be and what to do. If the polar low develops faster than predicted, that window is shorter. If the intensity is underestimated, the conditions at sea are worse than expected. These are not hypothetical scenarios. They are the conditions under which ships have been lost in the Barents, and they are the conditions under which ships continue to operate today. Wave heights in a severe Barents storm are another dimension of this. The Barents is a relatively shallow sea as Arctic seas go, with an average depth of around 230 metres and large areas of even shallower water over the banks. Shallow water affects waves in ways that are not always intuitive. In deep water, a wave of a given height has a certain wavelength, a certain distance between crests, and a certain period, the time between successive crests passing a fixed point. As waves move into shallower water, the wavelength shortens and the wave steepens. A steeper wave is a more dangerous wave for a vessel, because the slope of the wave face is greater and the forces acting on the hull are more abrupt. The Barents, with its combination of open fetch allowing long-distance wave generation, shallow banks where waves steepen, and the capacity to generate polar lows with high sustained winds, can produce sea states that are genuinely extreme. Wave heights of 10 to 14 metres have been recorded in severe Barents storms. These are not freak conditions. They are the upper end of what a bad winter storm in this sea looks like. There are also reports of rogue waves in the Barents, though rogue waves are, by their nature, difficult to document systematically. A rogue wave is typically defined as a wave that is at least twice the significant wave height of the surrounding sea, appearing with little warning. The mechanisms that produce them are still not entirely understood, though, wave focusing, the interaction of wave trains from different directions and certain current conditions are all thought to contribute. The Barents, with its complex bathymetry and the potential for wave energy arriving from multiple directions simultaneously, is the kind of environment where rogue wave formation is plausible. Whether individual ship losses in the Barents have involved rogue waves is often impossible to determine after the fact, because the evidence goes down with the ship. But the possibility is not dismissed by researchers who study wave dynamics in this region. There is another meteorological phenomenon specific to the area around Novaya Zemlya that deserves mention, because it affects navigation in a way that is easy to overlook. It is called the Novaya Zemlya effect, and it is a form of superior mirage caused by temperature inversion in the atmosphere. When a layer of warm air sits above cold air near the surface, light rays bend downward along the curvature of the Earth, allowing objects below the horizon to become visible, sometimes in distorted or duplicated form. The effect was first documented near Novaya Zemlya, which is how it got its name, though it occurs in other Arctic locations as well. The relevance for navigation is that the Novaya Zemlya effect can cause radar returns and visual sightings to be misleading. A coastline or an obstacle that appears to be at a certain bearing and distance may actually be somewhere else, because the image has been refracted. In an era of GPS and satellite navigation, this might seem like a historical curiosity, but radar interpretation in poor visibility still matters for collision avoidance and for navigating near ice. And an atmosphere that bends radar signals is an atmosphere that introduces errors into a system navigators depend on. The darkness is perhaps the most psychologically underestimated of all the Barents hazards, at least by people who have not experienced it. Above the Arctic Circle, which cuts through the southern Barents region, the sun does not rise at all during the depths of winter. At the latitude of Svalbard, roughly 78 degrees north, polar night lasts from late October to mid-February. For those 3.5 months, there is no daylight. Not reduced daylight, not short days, no daylight at all, daylightus. Navigation in those conditions relies entirely on instruments and artificial light. Assessing ice conditions visually is nearly impossible without floodlights. Reading the sea state, understanding what is approaching from upwind, judging distance and position relative to hazards, all of this becomes harder. The human body also responds to prolonged darkness in ways that affect alertness and judgment. fatigue accumulates differently. The sense of time distorts. Watchkeeping on a vessel in the Barents in January is a task that requires sustained mental effort in conditions that work against it. The cold compounds everything. At minus 15 degrees Celsius with a 30 metre per second wind, the wind chill is severe enough to cause frostbite on exposed skin within minutes. Maintenance tasks that would be routine in temperate conditions become difficult and slow when hands are encased in thick gloves and every surface is iced. Equipment that functions reliably at 0 degrees may fail at minus 20. Hydraulic systems, winches, hatch mechanisms, life raft release systems, all of these have operating temperature ranges, and the Barents in winter pushes against or beyond those ranges with some regularity. The spray icing problem mentioned earlier in connection with fishing vessels is part of this same picture. Ice accumulates not just on the hull and the rigging, but on everything exposed. Radar domes accumulate ice that degrades their performance. Antenna systems ice up. The weight of accumulated ice changes the vessel's stability in ways that the original design calculations did not account for, because the ice is not evenly distributed and it builds in ways that are hard to predict. Modern meteorological science has improved the situation considerably compared to what navigators faced even 50 years ago. The Norwegian Meteorological Institute operates dedicated Arctic forecasting services, and there are specific polar low warning systems that did not exist before satellite observation became routine in the 1980s. Vessels operating in the Barents today have access to forecast products that are substantially better than what was available to the trawlermen of the 1960s and 70s, or to the convoy escorts of the 1940s. The improvement is real, and it has saved lives. But there is a limit to what forecasting can do, and that limit is set by the physics of how polar lows form and develop. A system that can intensify in 12 hours in a region with limited surface observation density, over water that is itself changing as sea ice retreats and sea surface temperatures rise, is a system that will always carry forecast uncertainty. The models are better, but the phenomenon is not fully tamed. Meteorologists who specialise in Arctic weather are quite direct about this. The Barents remains one of the more challenging forecasting environments in the Northern Hemisphere, and the combination of rapid cyclogenesis, complex bathymetry, seasonal ice interaction, and extreme cold means that the margin between a manageable situation and a dangerous one can close faster here than almost anywhere else. What this means in practice for the people who operate in the Barents is that the sea demands a particular kind of attentiveness. Not paranoia, but a sustained awareness of conditions and a willingness to act on uncertain information. The experienced Barents navigator does not wait for certainty before making a decision about shelter or course change, because certainty often arrives too late. The decision has to be made on partial information, with the knowledge that the partial information may be wrong in either direction. The sea may turn out to be less severe than forecast, and the precaution was unnecessary, or the sea may turn out to be more severe than forecast, and the precaution was the difference. Living with that uncertainty, making those decisions repeatedly across a career is part of what it means to work in this sea. There is something worth sitting with in the fact that the Barents generates storms that are still not fully predictable, that it produces waves that can exceed the design limits of vessels built to operate there, that it creates atmospheric conditions that bend radar signals and reduce visibility to nothing for months at a time. None of this is supernatural. All of it has physical explanations, but the accumulation of those physical realities into a single body of water produces an environment that is genuinely formidable in a way that is hard to convey without going through the mechanics. The mechanics matter. They explain why the history of this sea is what it is, and why that history continues to be written. The storms are one layer of what the Barents is. Beneath the storms, beneath the surface, there is another dimension of the sea's character that has been accumulating for decades. One that involves not just weather and waves, but industrial infrastructure, economic pressure, and the specific question of what happens when something goes wrong, not on a ship but on the seafloor itself. The seafloor of the Barents Sea is not empty. It has never been empty. Not since the whalers of the 17th century began losing vessels to ice and storm. Not through the convoy years. Not through the Cold War decades when submarines slipped beneath the surface and sometimes did not come back up. But in the last 40 years, the seafloor has acquired a different kind of presence. Not just wrecks, but infrastructure. Pipelines, wellheads, subsea manifolds, the physical architecture of an industry that has decided the Barents holds something worth the effort of going to get it. The effort required is considerable. The Barents Sea sits at the edge of what industrial civilization can practically reach. The distances from shore-based infrastructure are not abstract. The Stockman gas field, which sits on the Russian side of the Barents, roughly 550 kilometers northeast of Murmansk, is one of the largest natural gas fields ever discovered. Its estimated reserves when it was first characterized in 1988 were around 3.9 trillion cubic meters of natural gas, along with significant condensate. That is a number large enough to be difficult to picture, but one way to put it is that Stockman alone contains more natural gas than the entire proven reserves of many mid-size producing nations. The Soviet Union identified it, the Russian Federation inherited it, and for decades the question of how to develop it at all in those conditions has been more complicated than the geology. On the Norwegian side of the median line, which divides the Barents between Norwegian and Russian jurisdiction, the Johan Castberg field sits roughly 240 kilometers northwest of North Cape, in waters about 370 meters deep. It was discovered in 2011, and it contains somewhere between 400 and 650 million barrels of recoverable oil, depending on which estimate you use. Norwegian oil company Equinor is leading its development, and first production was expected around 2024. The platform design for Johan Castberg is a floating production, storage, and offloading vessel, which means a large ship permanently moored over the field, processing oil and loading it onto tankers that come and go. That is the industrial reality of the Northern Barents, a floating city of workers, machinery and hydrocarbons operating year-round in conditions that the previous 9 sections of this story have described in some detail. The comparison that comes up most often when people discuss the risks of Arctic offshore drilling is the Deepwater Horizon blowout in the Gulf of Mexico in April 2010. That disaster killed 11 workers, released approximately 4.9 million barrels of oil into the Gulf over 87 days, and cost BP somewhere in the range of $65 billion in cleanup, legal settlements, and fines. It was, by almost any measure, one of the worst industrial accidents in American history. And it happened in the Gulf of Mexico, which is warm, well lit for most of the year, relatively close to the largest concentration of offshore oil service infrastructure in the world, and accessible to hundreds of vessels and thousands of workers within a matter of days. Now consider what a comparable blowout would mean in the Barents. The temperature of the water is between 0 and 4 degrees Celsius for most of the year. Ice may be present depending on the location and the season. The nearest major port with significant industrial capacity is Murmansk or Hammerfest, both of which are hundreds of kilometers away. The number of specialized vessels capable of responding to a subsea blowout and available in the region at any given time is a fraction of what was available in the Gulf of Mexico even at the beginning of the Deepwater Horizon response. And the environmental conditions that made the Gulf response difficult, wave action, currents, wind, would be substantially more severe in the Barents during any season except the brief Arctic summer. The specific technical problems with oil spill response in ice-covered or ice-affected water are not hypothetical concerns raised by environmental groups. They are documented limitations acknowledged by the industry itself and by regulatory agencies. Chemical dispersants, which were used extensively during Deepwater Horizon to break the oil into smaller droplets that microbes can degrade, behave differently in cold water. The microbial activity that breaks down dispersed oil is temperature dependent, and in near freezing water it is substantially slower than in the Gulf of Mexico. An oil slick that might degrade in weeks in warm water could persist for months in the Barents. Containment booms, the floating barriers used to corral surface oil so it can be skimmed or burned, cannot be deployed in pack ice. The ice moves, it breaks, it overrides the booms, and the oil moves with it or beneath it. Oil that gets beneath sea ice is extremely difficult to locate and nearly impossible to recover. It can travel under the ice for long distances, surfacing in places far from the original spill site, contaminating sea ice habitat that is critical for polar bears, ringed seals, and the entire food web that depends on the underside of the ice as a nursery for algae and small organisms. The window during which a surface response to a Barents spill would be practically effective, before ice conditions or weather make it impossible, could be measured in days. The Norwegian government has been navigating this tension for years, and the navigation has not been clean or comfortable. In 2020, the government approved an expansion of areas open to petroleum exploration in the Barents, including some areas in the southeastern Barents that had been previously off limits. Environmental organisations challenged the decision in court, arguing that it violated Norway's constitutional provision for a healthy environment. The case went through the Norwegian court system, reaching the Supreme Court in 2020, which ruled in favour of the government. The licences were upheld. The legal arguments were complex, turning partly on what the constitutional provision actually requires in terms of environmental impact assessment, and partly on whether the government's projections of climate impact from the extracted oil were calculated correctly. The court found in the government's favour on both points, but the case itself illustrated how genuinely contested the question is, even within a country that has built its modern prosperity on North Sea oil and has a sophisticated regulatory framework for offshore operations. The tension is not simply between industry and environmentalists, though that framing is the one that gets used most often. It is also a tension within Norway's own self-understanding. Norway operates the government pension fund Global, the world's largest sovereign wealth fund, which holds roughly $1.4 trillion in assets and was built almost entirely from oil revenues. That fund pays for Norwegian public services, healthcare, education and infrastructure. It is, in a very direct sense, what Norwegian oil money became. At the same time, Norway has committed to ambitious climate targets and positions itself internationally as a leader on environmental policy. Continuing to open new Arctic areas to drilling while simultaneously arguing for global emissions reductions is a position that requires a certain amount of cognitive flexibility, and Norwegian politicians are aware of it. The debate inside Norway about Barents drilling is genuine and ongoing, not a settled question. On the Russian side, the calculus is different in character, if not entirely in kind. The Stockman field has been the subject of development negotiations and planning for decades, but it has never actually been developed. The reasons are partly technical, partly economic, and partly geopolitical. The field is so remote and the development costs so high that it has never been economically attractive enough to proceed, especially after the shale gas revolution in the United States reduced global LNG prices in the early 2010s. Western sanctions following Russia's annexation of Crimea in 2014 and the much broader sanctions imposed after the full-scale invasion of Ukraine in 2022 have effectively cut Russia off from the Western technology and financing that Stockman development would require. The field sits there, enormous, cold, and for now unreachable in any practical sense. But other Russian Barents developments have proceeded. The Pryaslomnaya platform, which operates in the Pechora Sea at the southeastern corner of the Barents, became the first Arctic offshore oil production platform in Russia when it began producing in 2013. It is a fixed ice-resistant platform designed to withstand ice loads and extreme cold. In 2013, before production began, a Greenpeace vessel attempted to board the platform in protest, and the Russian Coast Guard arrested the 30 activists and crew members aboard the Arctic Sunrise. They were held for 2 months before being released. The incident drew international attention to the platform and to the broader question of Arctic offshore development, though it did not change the development timeline. What the Priraslomnaya operation represents in a practical sense is a proof of concept. It is possible to produce oil in the Barents. The platform has operated through multiple Arctic winters. The production volumes are not enormous, somewhere in the range of 2 to 3 million tonnes per year, but the operation exists and it functions. The question is not whether Arctic offshore oil production is technically possible. It demonstrably is. The question is what the risk profile looks like across a long operational lifetime, and what the consequences of a low probability but high consequence event would be in this specific environment. The people who think about this most carefully tend to use a phrase that comes from risk analysis: the response gap. The response gap is the difference between the time it takes for a blowout or major spill to develop into a large-scale environmental event and the time it takes to get effective response resources to the location. In the Gulf of Mexico, that gap was already large enough to cause catastrophic damage. In the Barents, the gap is wider by almost every measure. Distance, weather, ice, darkness, limited local infrastructure, the reduced performance of response equipment in extreme cold, all of these factors extend the time before an effective response is possible, while the spill itself continues to grow. There is one additional factor that does not get discussed as much as it should, which is the effect of extreme cold on the people doing the response work. Cleanup crews working in the Gulf of Mexico during Deepwater Horizon faced heat, sun, and difficult sea conditions. Cleanup crews working in the Barents in adverse conditions would face temperatures that can cause hypothermia within minutes of water exposure, winds that make working on deck physically dangerous, and darkness that limits visibility and increases the risk of accidents. The human element of a response operation is not separate from the environmental conditions. It is shaped by them at every level. None of this means that oil and gas development in the Barents is inherently reckless, or that it will inevitably produce a catastrophe. The Norwegian regulatory framework for offshore operations is among the most rigorous in the world, and the lessons of previous disasters, including Deepwater Horizon and the Alexander Kielland platform collapse in the North Sea in 1980, which killed 123 workers, have been absorbed into Norwegian offshore safety culture in ways that are real and measurable. The blowout preventer technology and well-controlled procedures used on Norwegian Barents operations are substantially more advanced than what existed in 2010. The monitoring systems, the emergency response planning, the well-designed standards, all of these are better than they were. But the Barents is also changing in ways that introduce new uncertainties alongside the improvements. The sea ice retreat that has been documented since the 1970s is continuing, and in some scenarios it continues quite rapidly. As ice retreats, areas that were previously inaccessible become accessible to drilling vessels. New fields that were under ice are now reachable. The opening of the Barents to navigation and extraction is happening faster than the regulatory and response infrastructure can fully keep pace with. The Norwegian Petroleum Directorate has been exploring areas in the northeastern Barents that were ice-covered as recently as the 1990s. The paradox is that the warming that makes climate advocates most concerned about Arctic drilling is also the warming that makes Arctic drilling more physically feasible. There is something quietly unsettling about that loop. The same process that is raising sea levels, disrupting ecosystems, and changing the fundamental character of the Arctic is also making it easier to extract the fossil fuels that drive that process. The Barents sits at the centre of that loop in a particularly visible way, because it is one of the fastest warming regions on Earth and one of the regions where new hydrocarbon extraction is most actively being pursued. Whether that constitutes irony or tragedy, or simply the ordinary logic of economic incentives operating in a changing physical environment, is a question that different people will answer differently. The sea itself does not have an opinion. What the sea does have is a set of physical characteristics that will not change, regardless of what decisions are made in Oslo or Moscow or corporate boardrooms. The polar lows will still form, the waves will still build, the temperatures will still drop to levels that challenge both machinery and human physiology. The distance from shore will still mean that response times are measured in hours, not minutes. The industrial presence in the Barents is growing, and the economic logic driving that growth is powerful, but the sea's indifference to that logic is total. It was indifferent to the whalers who came in the 1600s. It was indifferent to the convoy sailors in 1942. It was indifferent to the crew of the Kursk. It will be equally indifferent to a floating production platform in a polar low, or to a wellhead on the sea floor if something goes wrong 240 kilometres from the nearest port. The industrial chapter of the Barents story is still being written, and it is being written against a backdrop of improving technology, genuine regulatory effort, and real uncertainty about what the consequences of a serious accident in these waters would be. That uncertainty is not comfortable, but it is honest. And it sits alongside another kind of uncertainty, one that is less about industry and more about the fundamental question of what it means to operate in a place this remote, this cold, and this unforgiving, when something goes wrong and the clock starts running. That question of response, of rescue, of how quickly help can actually arrive when a vessel or a platform sends a distress signal into the Arctic darkness is one that the Barents forces into sharp focus in ways that calmer seas never quite do. So what does the response actually look like in practice when something goes wrong out there? The Norwegian Joint Rescue Coordination Centre, known as the JRCC, operates out of Bodø, a coastal city in northern Norway, and it is responsible for coordinating search and rescue operations across one of the largest SAR regions in the world. The area it covers extends from the Norwegian mainland far up into the Barents, across Svalbard, and out toward the edges of the Norwegian and Greenland seas. On a map it looks enormous, because it is. The coordinators working in Bodø are managing distress situations that can unfold hundreds of kilometres from the nearest helicopter base, in conditions that ground aircraft for hours at a time. There is a second coordination centre as well in Stavanger, which handles the southern Norwegian zones, but the Barents falls primarily under Bodø's responsibility. The centre runs around the clock, monitoring distress frequencies, tracking vessel positions through the automatic identification system, and coordinating with the Norwegian Coast Guard, the Royal Norwegian Air Force, and civilian helicopter operators who provide SAR coverage in the region. The helicopters are the critical piece. The primary SAR helicopter used in Norway is the Westland Sea King, which has been in service for decades and is gradually being replaced by the Augusta Westland AW101, a newer and more capable aircraft with longer range and better performance in severe weather. The AW101 can operate in conditions that would ground older aircraft, and its range is substantially greater, which matters enormously in the Barents. But range is only part of the equation. The other part is where the helicopters are based, because a helicopter that cannot reach a vessel in distress before the crew's survival window closes is, from a practical standpoint, not close enough. Longyearbyen, the main settlement on Svalbard, sits at roughly 78 degrees north. It has a helicopter base with SAR capability, and for vessels operating in the central and northern Barents, it is often the closest point from which a rescue aircraft can be launched. Depending on where exactly a vessel is in distress and what the weather is doing, the flight time from Longyearbyen can range from about 45 minutes to well over 2 hours. In some parts of the Barents, particularly the northeastern areas near Novaya Zemlya or Franz Josef Land, even the Longyearbyen base is too far for a helicopter to reach within a meaningful survival window without the vessel's crew having access to survival suits and life rafts. This is where the math of survival becomes very direct and very uncomfortable. Water temperature in the Barents Sea ranges from roughly 0 to 4 degrees Celsius in most areas during most of the year. At 0 to 2 degrees, which is common, a person in the water without a survival suit will experience cold shock within the first 30 seconds, which can cause uncontrolled gasping, hyperventilation, and cardiac stress. Swimming capacity is lost within minutes as muscles cool and stop responding effectively. Incapacitation, meaning the inability to keep one's airway above water, typically follows within 10 to 15 minutes. Death from drowning or cardiac arrest generally occurs within 30 minutes, though individual variation exists and some people have survived longer. A survival suit changes the numbers significantly. A properly worn immersion suit can extend survival time to several hours because it traps a layer of water against the body that warms to body temperature and provides insulation. But survival suits must be put on before entering the water, which requires time and the physical ability to do so. In a sudden capsize or catastrophic flooding event, there may not be enough time. In the chaos of a vessel going down in a storm, suits may not be accessible or may be put on incorrectly. The survival time extension that a suit provides is real, but it depends on a chain of conditions that are not always met. The Cospas SARSAT satellite system is the backbone of distress alerting in the Barents and across the global ocean. When a vessel's emergency position indicating radio beacon, the EPIRB, is activated, either manually by the crew or automatically when the device is submerged, it transmits a signal on the frequency of 406 MHz. That signal is picked up by a network of satellites in low Earth orbit and geostationary orbit, processed to determine the beacon's location, and relayed to a local user terminal, which then passes the alert to the relevant rescue coordination centre. The whole process, from beacon activation to alert reaching the JRCC in Bordeaux, can take as little as a few minutes with the right satellite geometry. Modern EPIRBs also incorporate a GPS receiver, which means the location they transmit is precise to within about 100 metres rather than the several kilometres that older systems could achieve. That precision matters enormously in a search and rescue operation, because it means the helicopter or Coast Guard vessel is being directed to a specific point rather than a search area. The difference between a precise location and a search area in the Barents, in the dark, in a storm, can be the difference between a rescue and a recovery. But the system has limits. An EPIRB only activates if someone turns it on, or if it is submerged, which means it works best in a sinking scenario where there is time for the device to deploy. In an explosion, a catastrophic structural failure, or a very rapid capsize, the EPIRB may not activate at all, or may activate too late. The Kursk's distress signals were confused and delayed, and that was a large submarine with extensive communications equipment. A small fishing vessel that goes down in 3 minutes in a polar low may not transmit anything useful before it is gone. The Norway-Russia cooperation framework for search and rescue in the Barents is actually one of the more functional bilateral agreements between the two countries, even during periods when the broader political relationship has been strained. The two countries signed a joint SAR agreement in 1995 that defines areas of responsibility and establishes protocols for coordinating rescues that cross the boundary between Norwegian and Russian SAR zones. In practice, this has meant that Russian Coast Guard vessels and helicopters have assisted in rescues on the Norwegian side of the boundary, and Norwegian assets have operated in Russian zones when the situation required it. The agreement was tested in various incidents over the years, and by most accounts it has worked reasonably well at the operational level, meaning the people actually coordinating rescues have generally been able to communicate and cooperate even when the political atmospheres above them were difficult. Whether that cooperation would survive a more serious political rupture is an open question, but for now it represents one of the few areas of genuine practical collaboration between Norway and Russia in the High North. The Norwegian Coast Guard itself maintains vessels permanently stationed in the Barents region, including the ice-capable KV Svalbard, a large offshore patrol vessel that can operate in moderate ice conditions and serves as a platform for SAR, fisheries inspection, and environmental response. The KV Svalbard was commissioned in 2002 and represents a significant capability, but it is one ship covering an enormous area. When it is on the far side of its patrol zone, Response times for vessels in distress on the other side can still be measured in many hours. What has genuinely improved over the past few decades is the quality of information available before something goes wrong. Meteorological forecasting for the Barents has advanced substantially since the 1980s, partly through better satellite coverage, partly through improved numerical weather prediction models, and partly through a denser network of weather buoys and automated stations on Svalbard and the surrounding islands. Polar lows, those compact and violent cyclones that can develop within 24 hours over open water, are now detected earlier and tracked more reliably than they were even 20 years ago. The forecasts are not perfect, and polar lows still retain the capacity to surprise, but a vessel that is paying attention to modern weather data has significantly more warning time than vessels did in earlier eras. The vessel monitoring systems used by the Norwegian fishing fleet also represent a real safety improvement. Norwegian fishing vessels above a certain size are required to carry automatic identification system transponders and vessel monitoring system equipment that reports their position to fisheries authorities at regular intervals. In theory, this means that if a vessel stops reporting, someone notices. In practice, the monitoring is not always real-time, and the gap between a vessel going silent and someone initiating a response can still be long enough to matter. There is also the question of what happens after a rescue helicopter arrives on scene. Finding survivors in the water in the Barents at night, in a swell, is genuinely difficult work. The helicopter crew is looking for heads in dark water, possibly with lights if survivors have them, possibly without. The rescue swimmer who enters the water to assist survivors is working in conditions that are physiologically hostile even in a survival suit. The hoisting process, getting a survivor from the water into the helicopter, requires the survivor to have enough physical function to cooperate, which may not be the case after even a short immersion in near-freezing water. Every step of the rescue process is harder in the Barents than it would be in warmer, calmer waters, and the training and equipment that SAR crews bring to those operations reflects the understanding that the margin for error is small. The survival suit requirement for commercial fishing vessels operating in Norwegian waters has been in effect for years, and compliance is generally high within the Norwegian fleet. The Russian fishing fleet operating in the same waters has had a more inconsistent record on safety equipment, partly because of the older average age of the vessels, and partly because of differences in regulatory enforcement. The gap in safety culture and equipment standards between the Norwegian and Russian commercial fleets operating in the same body of water has been a quiet source of concern among maritime safety researchers for a long time. There is something worth sitting with in all of this, which is that the infrastructure for responding to disaster in the Barents has improved enormously compared to what existed even 30 years ago, and yet the sea's fundamental character has not changed at all. The helicopters are faster and more capable, the beacons are more precise, the forecasts are better, the coordination agreements are in place, and still, the basic arithmetic of survival time versus response time in the central and northern Barents means that for certain scenarios, in certain locations, the outcome of a catastrophic event is largely determined before the rescue centre even receives the alert. This is not a criticism of the people who operate the SAR system. It is simply a description of what the Barents is. It is a sea where the distances are large, the conditions are severe, the survival windows are short, and the combination of those three things creates a category of risk that infrastructure can reduce but cannot eliminate. The JRCC coordinators in Bodo know this, the helicopter crews know this, the fishermen who have worked the Barents for generations know this. The knowledge does not make the sea safer, it just means that the people who go there understand what they are accepting, and perhaps that understanding is part of what makes the Barents so quietly striking as a place. It is not a sea that allows comfortable illusions about human control. Every improvement in technology and coordination is real, and matters, and has saved lives that would otherwise have been lost. But the sea absorbs those improvements and continues to be what it is. The polar lows still form in less than a day. The waves still build to 12 and 14 metres, The water temperature at the surface in January is still within a degree or two of freezing. The nearest hospital is still hours away by air, and only if the air is flyable. There are currently hundreds of wrecks on the Barents Sea floor, from wooden hulls that have been there since the 17th century to steel vessels that went down within living memory. Some of them carry cargo that has never been recovered. Some of them carry people. The sea holds all of it with the same indifference, and the SAR infrastructure that exists today is in many ways a long ongoing argument with that indifference, an attempt to narrow the space between what the sea can do and what humans can prevent. It is an argument that has made genuine progress, but it is also an argument that the sea has never agreed to participate in, and that asymmetry is what gives the Barents its particular weight. The helicopters are ready in Longyearbyen. The EPIRB signals are being monitored. The Coast Guard vessels are on patrol, and somewhere out in the northern Barents right now, there are vessels working in conditions that would be considered extreme almost anywhere else on Earth, and the distance between them and help is measured in hours that the water temperature does not allow. That gap, that irreducible distance between the human effort to respond and the sea's capacity to overwhelm, runs through the entire history of the Barents. It ran through the whaling era and the convoy years and the Cold War submarine operations and the Kursk and the fishing fleet losses that never made international headlines. It runs through the oil and gas development that is expanding into the northeastern Barents today. And it will run through whatever comes next, because it is not a product of any particular era or technology or political arrangement. It is a product of what the Barents is and what it has always been. Which brings us finally to the question of what the Barents means, not just as a place of danger and resource and history, but as a place that has accumulated all of that over centuries and holds it, quietly, beneath the surface. There is a particular kind of place that does not announce itself the way famous places do. It doesn't have a striking skyline or a name that carries immediate weight in conversation. Most people could not point to it on a map without pausing, and yet it has shaped events, consumed lives, held secrets, and continued doing all of those things across centuries without any particular need for recognition. The Barents Sea is that kind of place. It has been working quietly at the edge of human history for as long as humans have been bold or desperate enough to go there, and it will continue doing so long after the current generation of vessels working its waters has been replaced by whatever comes next. When you try to hold the full picture of the Barents together in your mind, what strikes you is not any single disaster or era or feature, but the continuity of it. The same basic forces that killed Willem Barents and his crew in 1597, the ice, the cold, the distance from help, the speed with which conditions can change, are the same forces that sank the Kursk in 2000 and that continue to take fishing vessels today. The technology has changed enormously. The geopolitical context has shifted several times over. The industrial infrastructure on and around the sea has grown from a handful of whaling stations to offshore drilling platforms and nuclear submarine bases. But the sea underneath all of that activity has remained essentially constant. The polar front still sits where it sits. The polar lows still form without warning. The water temperature in the northern Barents in winter is still close enough to freezing that the difference is academic for anyone who ends up in it without a survival suit. What the Barents holds on its sea floor is, in a strange way, a kind of archive. Not an organised one, not one that anyone designed or intended, but an archive nonetheless. Down there, in water that ranges from a few dozen metres to several hundred metres deep depending on where you are, there are wooden hulls from Dutch and English whalers that went down in the 17th century, their timber slowly becoming part of the sediment, their cargo of whale oil long since dispersed into the water column. There are merchant ships from the Arctic convoys of World War II, some of them still carrying the tanks and aircraft and vehicles that never reached Murmansk, resting in the same positions they settled into when they were torpedoed or bombed or overwhelmed by the weather in 1942 and 1943. There are Soviet fishing trawlers from the post-war decades, and Norwegian vessels that capsized in polar lows that gave almost no warning. And there are submarines, some of them carrying nuclear material that has not gone anywhere and is not going anywhere, because the sea does not return what it takes. The Komsomolets is one of the most closely watched of these wrecks. The Soviet submarine sank in April 1989 in the Norwegian Sea, at the boundary of what is considered the broader Barents region, after a fire broke out on board. 42 of her crew of 69 died, many of them in the water after the submarine sank, because the rescue response was slow and the water was what the water always is. The Komsomolets rests at roughly 1,680 metres depth, and she's carrying 2 nuclear-tipped torpedoes. Russian and Norwegian scientists have been monitoring the wreck for decades, taking water samples around the site, measuring for signs of radioactive leakage. The results over the years have been mixed and sometimes concerning. There have been readings near the torpedo tube suggesting that some corrosion and leakage is occurring, though the assessments of how serious this is and what the long-term trajectory looks like have varied between the Russian and Norwegian scientific teams involved. What is not in dispute is that the wreck is there, that it contains nuclear material, and that the sea is slowly doing what the sea does to metal over long timescales. The monitoring continues because the alternative, not monitoring, is not acceptable. But monitoring is also not the same as being able to do anything about it, and that gap between watching and acting is a quiet symbol of something larger about the Barents. The sea holds things that we cannot retrieve and sometimes cannot fully understand, and the best available response is careful attention and the hope that the timescales involved are long enough that the problem remains manageable. There is something almost philosophical about that situation, though it does not require grand language to describe. It is simply the reality of what happens when human activity at industrial and military scale takes place in an environment that is not forgiving of mistakes and does not offer easy recovery options. The Barents has been the site of that kind of activity for a long time now, and the accumulation of what has been lost there, the ships, the people, the cargo, the submarines, the nuclear material, is a physical record of the cost of operating in a place like this. It is not a record of failure, exactly. Most of the people who went into the Barents across those centuries went because they had real reasons to go. Because there were fish to catch, supplies to deliver, nations to defend, resources to extract. The losses were not the result of carelessness in most cases. They were the result of the sea being what it is, and the gap between what humans could manage and what the Barents could produce being, at critical moments, wider than anyone could bridge. The people who work the Barents today carry some version of that history with them, whether they think about it explicitly or not. The Norwegian Coast Guard officer on patrol in the northern Barents is operating in the same water where convoy escorts watched merchant ships go down in 1942. The Russian fisherman working the cod grounds near the central bank is working in a tradition that stretches back through the Soviet trawler fleets and further back to the Pomor traders, who navigated these waters in wooden boats using knowledge that was passed from one generation to the next, because writing it down was less reliable than living it. The petroleum engineer on a platform in the southwestern Barents is working in a sea that has been economically important for 4 centuries, just in a different way than it was before. The continuity is real, even when the people involved are not thinking about it. What the Barents asks of all of them, in different ways, is a particular kind of attention. Not fearlessness exactly, because the people who work there long enough develop a very clear-eyed respect for what the sea can do. Something more like sustained alertness, the willingness to take the forecast seriously even when the sky looks fine, the habit of checking the survival suit before going on deck, the discipline to turn back when the conditions say to turn back, even when the fishing is good or the schedule is tight. These are not dramatic qualities. They are quiet ones, the kind that do not make for good stories but that account for the difference, in many cases between a voyage that ends normally and one that does not. And the Barents does end voyages normally, far more often than it ends them catastrophically. It is worth saying that plainly because the weight of the history and the scale of the losses can create a picture of a sea that is simply lethal, which is not quite right. Hundreds of vessels work the Barents every year, fishing and patrolling and supplying the communities on Svalbard, and transiting between Norwegian and Russian ports, and most of them complete their work and return without incident. The sea is not hunting them. It is not hostile in any directed sense. It is simply operating according to its own physics, which are indifferent to human purposes and human schedules, and the people who work it successfully are the ones who have learned, through training or experience or both, to work within those physics rather than against them. But the indifference is real, and it is worth dwelling on for a moment. The Barents does not distinguish between a ship that deserves to survive and one that does not. It does not factor in the experience of the crew, or the quality of the vessel, or the importance of the mission. A polar low does not pause because the ship in its path is carrying medical supplies, or because the crew has families waiting for them. The wave that builds to 12 meters in a severe storm does not check whether the vessel in its path has modern stability systems or an older hull that was not designed for those conditions. The water temperature does not adjust because the person who has just gone into the water is a skilled sailor who has spent 30 years at sea. The sea applies the same forces to everyone, and the outcomes depend on preparation and equipment and the specific timing of events, and, at the margins, on luck. That combination of factors is not unique to the Barents, but the Barents applies it at an intensity and in a context that leaves very little room for the luck to compensate for gaps in the other categories. That is, in the end, what makes the Barents so hard to forget once you have spent time thinking about it. It is not the most dramatic sea in terms of wave heights, though its storms are severe. It is not the coldest sea on Earth, though it is cold enough. It is not the most remote, though its distances are real. What makes it striking is the combination. The way the physical extremity intersects with centuries of human necessity. The way the economic and military importance of the sea has kept drawing people into it, regardless of what it costs. The way the losses have accumulated quietly across 400 years without ever making the sea less essential to the people who depend on it. The Barents has been a place where the stakes were high and the margin was thin for a very long time, and it continues to be that place today. The wrecks on the seafloor are not going anywhere. The Komsomolets will continue to be monitored. The Johan Castberg field will begin producing oil, and the question of what a blowout response would look like in ice-covered water will remain an open one that the industry and regulators are working through with the knowledge that there is no fully satisfying answer. The fishing fleets will continue to work the cod and haddock grounds, and the polar lows will continue to form in less than 24 hours, and the SAR helicopters in Longyearbyen will continue to be ready. The sea will continue to warm faster than almost anywhere else on Earth, and the ice will continue to retreat, and new areas that were previously inaccessible will become accessible, and the question of what that means for the people and vessels moving into those areas will continue to be worked out in real time. None of this is tidy. The Barents does not offer tidy conclusions. It offers a long continuing story about what happens when human beings need something that can only be found in a place that does not accommodate them easily, and about the particular kind of persistence and cost that story involves. If you have been listening tonight from somewhere warm, from somewhere where the temperature outside is comfortable, and the nearest emergency services are close, and the water, if there is any water nearby, is not cold enough to incapacitate a person in minutes, then perhaps the Barents feels like a very distant place. And in physical terms, for most people listening, it is. But it is also a place that has shaped the history of the Arctic, of World War II, of the Cold War, of the global fishing industry, and of the ongoing question of how human beings will manage the resources and risks of a warming Arctic. It is closer to the present and to the future than its remoteness might suggest. Thank you for spending this time here tonight. If something in this story stayed with you, whether it was the convoys, or the Kursk, or the quiet ongoing watch over a sunken submarine carrying nuclear warheads in water that is very dark and very cold, I would genuinely like to hear about it in the comments. These are the kinds of places and stories that deserve more attention than they usually get, and knowing what resonates with you helps shape what comes next on this channel. If you have not already, A like on this video and a subscription to Life Beyond Seen means a great deal, and it helps this kind of quiet, careful storytelling find the people who are looking for it. The Barents Sea is not cruel. It has never been cruel. Cruelty requires intention, and the Barents has none. It is simply a body of water doing what bodies of water do, on a scale and at a temperature, and in a location that makes the consequences of being there, and of things going wrong there, very serious indeed. That indifference, that complete absence of malice or mercy, is what has defined the Barents across all the centuries of human contact with it. And it is, in the end, what makes it so difficult to look away from. The sea does not care whether you understand it. But there is something in the understanding, something in sitting with the full weight of what that water holds and what it has asked of the people who have crossed it, that feels worth doing, quietly, carefully, from a safe distance, which is perhaps the only sensible way to regard the Barents at all.